started. A bit late, but better late than never. How do I get rid of this thing? Okay. Is the video working? Oh. Okay, as long as it's working, that's good. Let me get it. Yeah, if I don't check online and on Zoom, hide video panel. Okay. Yeah, when you tell me it's good, then we can start. Okay, it's good. Okay, let's get started. Oh, it's not too late. Yeah. There are too many deadlines these days, so it's always tough to make it to meetings, let's say. But I didn't forget the lecture. Okay, today we're going to cover another topic that was promised, cache coherence. Just to give you an idea, today we'll cover cache coherence. Hopefully we'll finish it. And then tomorrow we'll cover interconnects. Probably we'll have another lecture on interconnects because interconnects is actually such a big topic that you can cover it for an entire semester. I mean, even cache coherence, you can make an entire semester's topic. There's so much literature on this, but we'll dedicate only one lecture to this topic. It's a very traditional topic. And then hopefully we will cover bottleneck acceleration. And then we'll have a bunch of discussion sessions before the exam. Does that sound like a good plan? And we can put some optional videos for you to watch also, maybe some optional lectures, maybe some research lectures, but they will not be related to the exam in general. But these topics will be on the exam. Not that you should be optimizing for the exam. These are some fundamental topics that is important to know, as you will see. Okay, any questions? Okay, just to give you let's say, warm up your caches. We were talking about weak memory ordering in the last lecture, and we talked about weak memory ordering. I will briefly go over that to see if you have any questions. If not, we will move on to cache coherence. But basically, we discussed sequential consistency, where we discussed why it's important, and we discussed that there are some issues with it. It's too strong of an ordering requirement, basically. It imposes that every memory access should be seen in the same order by every processor in the system. And this is, in general, not easy to do if you have a large-scale system especially. But even in a small-scale system, it becomes very wasteful. And usually it makes out-of-order execution and caching type of techniques complicated because these actually reorder the requests or hide the requests from different processors. So that's why sequential consistency is not that desirable. And as a result, people have developed weaker memory consistency techniques. It's a bit slow, so I'll go through this quickly because you've already seen all of these slides, actually. Essentially, here, the idea is to specify regions in which memory operations do not need to be ordered. And some instructions delineate those regions, memory fence operations. And these fence operations essentially are memory barriers also, as we discussed. All memory operations before the fence must be completed, before the fence is executed. And all memory operations after the fence must wait for the fence to complete. And fences complete in program order. And all synchronization operations act like a fence. And then we discussed that people have discovered that you just need to have fences at synchronization points in the programs. So we discussed this beautiful paper. I would recommend you actually review it in your homework. It's an optional paper. But basically, this paper explains the problem in a very nice way, I would say. So for example, under SC, sequential consistency, every access within the critical sections is delayed until the previous access completes. But such delays are unnecessary if the programmer has already made sure that no other process can rely on the data structure to be consistent until the critical section is exited. And you can see, again, the ordering. And then basically this paper goes on release consistency work actually goes on and sees that actually the operations after the release do not need to wait as well. So they propose an even weaker consistency model, and they basically realize that the purpose of the release is to signal that previous accesses are complete. And it does not have any anything to say about the ordering of the accesses following it. So it doesn't have any bearing about the accesses that come after it. The accesses that come after it are not on shared data, essentially, until you get another synchronization operation. So basically, people have realized that if you mark the synchronization operations and just order them in your memory consistency model, then that's enough. As long as you're perfect at marking your synchronization operations. If you actually miss a synchronization operation, then you have a problem, right? So that's why this is actually interesting, but it creates a trade-off now. So basically, weaker consistency, there's no need to guarantee a very strict order of memory operations. As a result, it enables the hardware implementation of performance-enhanced techniques like out-of-order execution caching to be simpler. And it can be higher performance than stricter ordering, as people have shown. But the disadvantage is it imposes a lot of burden on the programmer. I'm going through relatively quickly because we discussed a lot of these actually. Now the programmer needs to get the fences and the labeling of synchronization operations correct. Especially if you go weaker and weaker and weaker, this becomes harder and harder and harder, because if you forget something, then you may actually have bugs. This is like forgetting a lock in a sense, right? Forgetting a lock is a higher level issue, right? Of course, if you forget a lock, you're forgetting a high level synchronization operation. If you forget marking a synchronization operation as a synchronization operation, it's a lower level issue. Basically, you may run into problems with memory ordering because memory ordering is assuming that you actually mark a synchronization operation as a synchronization operation. If you forget to mark it, then it's not going to impose an order, and you may actually get the wrong. Essentially, two processors can be in the critical section because you're not actually marking your synchronization operations correctly. Okay, so there's more burden on the programmer or software essentially, and also debugging is harder because now it's harder to reason about what went wrong. Actually, compared to sequential consistency, debugging is much harder because now the ordering is actually much more relaxed. So the baseline that you're thinking about when you're debugging your program, if you have a bug, for example, if you forgot to lock a synchronization, forgot to mark a synchronization operation, for example, it's very difficult to find it right now. So this point we didn't make very clear, I think, the last time, but I think debugging becomes harder as you make your ordering, memory ordering, weaker and weaker. Make sense? But there's another form of debugging that we discussed as debugging across runs of a program. That's always hard, basically. And that becomes a little bit harder basically sequential consistency doesn't say anything about ordering, how operations are ordered across different runs of a program, meaning that a bug that may exist, a synchronization bug at the high level, that may exist at a low level, may be present in one ordering, in one run of the program, but it may not be present in the second run of the program, in the third run of the program, basically. So there are multiple debugging issues to consider here. Can you actually replicate the bug across different runs? Or within a single run, can you actually try to figure out what's going on, basically? So here, debugging is harder in both perspectives in the end, when you go to weaker consistency models. So, okay, this is another example of the programmer microarchitect trade-off. In a kind of a different way, basically. If you actually make the consistency model weaker, programmer's job becomes harder, microarchitect's job becomes easier. We talked about, for example, virtual memory. Virtual memory is another example of programmer microarchitect trade-off. Enabling virtual memory helps the programmer significantly, but hurts the microarchitect a lot. So in the end, it's really about an issue of programmer convenience versus microarchitect's convenience. Okay, any questions? Yes, quickly.
My question is, do you see
I see, yeah. Yeah, I mean, it's possible. People have proposed in research literature, there are actually a lot of proposals for things like record and replace. Those are usually called record and replace. This is the ordering that I've seen in this run. So in the next run, I'm going to enforce that ordering also happens, and usually hardware keeps track of that. But there are also software proposals. Software can actually keep track of that also. Of course, software proposals are much higher overhead in terms of debugging. So hardware support is in general much better for these things, because otherwise your debugging time also quite increases significantly. And with complex programs, debugging compilation loop is actually very, very long in general. So I think it's good to research these things, but they may have limited adoption in real life. But it's useful, I think, in general. If you've done multi-threaded programming, you would really like to at least keep some things constant. And if the order is not constant, then you actually are trying to debug things in a difficult way. Okay, and then we discussed that this paper actually shows that if you use speculative execution and prefetching, you can actually get the performance of weaker models while preserving sequential consistency. Of course, this complicates the hardware, but again, I'm not going to talk about this. So this is a beautiful paper. Again, this is on your reading list if you're interested in doing a bonus reading on this one. I like this paper because there's been a lot of research on this topic, but this paper's conclusions actually remains quite significant, even though it's more than 30 years old, as you can see. Other papers actually in recent times confirmed this paper's intuition, not intuition, just also results. Okay, any questions? Any other questions on memory consistency or memory ordering? Okay, now let's jump into cache coherence then. Cache coherence is going to be a similar problem in multiprocessors, but in a very different way. And we've already distinguished it. I'm going to distinguish it a little bit more. Essentially, this happens because you cache data. And caching not only contemplates ordering of all operations, like we discussed earlier. A memory location can be present in multiple caches. And this is also shown earlier. This prevents the effect of a store or load to be seen by other processors. As a result, global ordering becomes difficult, right? But it also complicates ordering of operations on a single memory location. And cache coherence is all about a single memory location. We're going to talk about that, or a single cache block, if you will. A single memory location can now be present in multiple caches. And now this makes it difficult for processors that have cached the same location to get the correct value of that location. For example, if one processor updates that location, writes to that location, another processor needs to be aware of it if it wants to get the correct data, right? And usually you rely on getting the correct data. If it's a shared data, for example, or if it's a lock synchronization, if it's a synchronization metadata or shared data, you really want to get the correct data. Okay, so that's the problem basically. So let's discuss the differences. I think we already had the slide earlier, but consistency, what we discussed in the last lecture, is about ordering of all memory operations from different processors to different memory locations. It's really about the global ordering of accesses to all memory locations. That's why we had in the sequential consistency, we had the switch, right? The memory it serves different processors as a switch. As a result, everybody sees the same global ordering. Cache coherence, it's related, but it's different. It's about ordering of operations from different processors to the same memory location. So it's about memory location X. It doesn't consider memory location A, B, C, D, E, F, as we discussed last time, right? It's local ordering of access to each cache block, essentially. And you want to keep that consistent across processors. Unfortunately, the naming is a bit unfortunate because some people call this cache consistency also. And memory consistency is never called memory coherence, but it's called memory consistency. So sometimes you may get confused. So I will call it cache coherence. I will not call it cache consistency. But in a sense, it's about consistency to the single memory location in the end. Okay, so we're going to see a difference. And these are also related, in fact. In existing processors, to satisfy some of the consistency, you make use of coherence protocols like we will discuss later on. So they're not unrelated topics completely, but fundamentally, they're different concepts. Okay, so there are a bunch of readings, as I mentioned earlier. Well, I guess these are, I didn't mention, but these are some, it says required, but again, it's optional readings. You can, if you read them, you will understand things better. There's a book, Parallel Computer Architecture. It's relatively old right now. It's written in 1994, I think. I don't know if they released an updated version. It talks a lot about these issues, and there are some chapters that actually explain cache coherence quite nicely, and I will borrow some material from them also. And then this is the paper that introduced the MESI protocol that we will discuss. And then there are a bunch of other papers that I will mention or not mention, but I would recommend you take a look at it. Some of these are in your optional homework. Some of these we didn't add, but if you're interested, you can take a look. Okay, so essentially we're talking about the shared memory multiprocessors again. This is tightly coupled multiprocessors, and we're communicating through shared memory. Let's say processor 0 writes to an address, followed by processor 1 reading from that address. This implies some communication between the two, right? Again, this communication may be synchronization or maybe some shared data update. And you can see this is an example, right? Processor 0 writes something, processor 1 prints that location. Here, each read should receive the last value written by anyone, right? And this requires some sort of synchronization. So the question is, what does last written mean, right? That becomes a question also, right? If you conceptually can order this memory A equals 1 after here, then maybe this is, if you didn't synchronize between the two, for example, what may happen is old value of memory A may be printed, and that may be okay, right? If depends on the synchronization, basically. it depends on the intent. What value this should get is depending on the synchronization that's programmed by the programmer between these two different threads. So assuming that the synchronization requires that this value should be printed, so there's some synchronization that makes sure that this, for example, this is shared data. This processor cannot print before this processor updates the data, because there's a lock that protects the critical section. Clearly, this is shared data. Then this processor must print 1, right? Assuming these are the only threads. But of course, caches complicate the problem, right? What if memory A is cached at either end? If this processor cached memory A and it has the value 0, it may print 0, right? But of course, that would be wrong, right? Given that the program is synchronized the way I mentioned, processor 1 should not print 0. It should really print 1. But caching complicates the issue, basically. So basically, the problem is with caching. If multiple processors cache the same block, how do they ensure that they all see a consistent or coherent state? So this is a simple example. You have, let's say, processor 2 loading a main memory location X, and the value is 1000. It did that load. And then processor 1 does the same load. Both of them have 1000, and everybody is correct right now, right? And then processor 1 does something to that memory location and updates it, makes it 2000. And then processor 2, assuming that there's some synchronization that happened, which I'm not showing over here, processor 2 loads that location again. At that point, it should not load 1000, right? Makes sense, right? Again, this is assuming that there's some synchronization that happened in between that requires that processor 2 should get the updated value, right? If that synchronization wasn't there, maybe it's okay, right? Because again, if you do not properly synchronize your program, essentially the outcome is dependent on what may happen. The outcome is dependent on the ordering. So all of this assumes proper synchronization, just like I've assumed in memory ordering, right? I assume that, I'm going to assume that over here. There's proper synchronization that requires that this should not load 1000. So even if you're properly synchronized, though, this may load 1000 if this value of this update doesn't get communicated to this cache, right? And in this particular case, I didn't communicate it clearly. Okay, so that's the problem. Hopefully that makes sense, right? How many people have seen cache coherence in a past lecture? Okay, how many people have not seen it? Again, don't be shy, it's okay. Okay, yeah. I mean, these don't get covered, especially, I mean, even in digital design and computer architecture, which is an extensive course, we cover it very little. I just introduced the problem and we don't really talk about solutions, right? So if you've taken digital design and computer architecture, you've seen the slide, but not to this detail, of course. Okay, then the question becomes, who should really make sure that this processor 2 doesn't load 1000, doesn't load the wrong value from the cache, basically? Okay, we're going to briefly discuss software approaches and dismiss them, because this is very hard for purely software approaches. Software-hardware cooperation may be possible and may be desirable in the future, but it makes programmers' life tougher. We're going to talk a lot about hardware approaches later on. So basically, the key question with software approaches is, can the programmer ensure cache coherence if the caches are invisible to software? Well, that's a tough thing, basically. If the caches are invisible, how do you actually invalidate the caches, for example? How do you make sure that? So you need to have some notion of caching, basically, to be able to do that. So people have developed coarse-grained coherence mechanisms, which is page-level coherence at the virtual memory level, for example. You lock a page so that no one has access to that page. That's a possibility. But even then, at some level, it requires that locking requires some hardware support, basically, underneath. So purely software solutions are impossible, I would argue here. You can imagine them maybe, but always there's some catch there. Non-solutions make shared locks and data non-cacheable. Basically, essentially, when you're synchronizing, when you're locking some data structure, you say that they're not cacheable. There's only one place where they can be updated in the memory, and I will call this a non-solution immediately because this is really bad for performance. Clearly, you don't want to do that, right? That's one way of actually making software solutions potentially work. Again, we didn't work out the details, but that's essentially you can do that. You can say everything is non-cacheable in the end, and that eliminates the problem, right? That doesn't sound good. Or you can say everybody has the same cache. Everybody sees the same cache. That also eliminates the problem, but that's also a non-solution, right? We cannot build a huge cache across 10,000 processors. That's shared, basically, completely. Okay, so basically a combination of non-cacheable and coarse-grained is potentially doable, which requires some hardware support still. but it's very, very difficult for the programmer. Meaning, what does this mean? Basically, you ensure that your synchronization operations are not cached. They're always updated in memory. And then you do coarse-grained page locking. And if you do all of this, maybe you can make it work. But the problem is, if you do that, there's a lot of overhead also, right? Because one processor wants to write to one location in this page, and this other processor wants to write this other location in this other page. They cannot concurrently access the page, even though these may be completely different locations, right? So page-level coherence, coarse-grained coherence has a lot of overheads in that sense. Now, if you wanted to go fine-grained, meaning say, I want to do this at a fine-grained level. I don't want to lock pages. I want to lock cache blocks, let's say. And I want to ensure that the cache blocks are properly flushed and invalidated using software so that I can ensure that this poor processor doesn't load 1000. Now you need to think about instructions like this, potentially, like flush local, for example. You can imagine some instructions that flush invalidate the cache block containing address A from a processor's local cache. Or you can imagine a flush global instruction, which flushes invalidates the cache block containing address A from all other processors' caches. So for example, if you go back to this picture, if this processor, after or while it wrote to 2000, if it also sent a flush global, all of the other processors would receive the flush global and they would invalidate this block so that no one would have 1000 anymore, right? That sounds good. That sounds good until you start considering, what if someone else executes another instruction that loads that location after that flush global happens, but before the write happens? So you run into race conditions, basically. Once you start doing that sort of solution in software, you run into a lot of race conditions because you're not atomically doing these updates in the end. And then you can also go heavy-handed and say flush the entire cache, right? Invalidate all the blocks in my cache. Again, this doesn't solve the problem completely. So basically, you need to have hardware support if you want to go fine-grained, and you can think about it a little bit. But it's basically a lot of people have thought about it and figured out that you really need to have some hardware support. And okay, even if you make it work somehow, this becomes a disaster from the programming perspective, right? Now the programmer needs to know about caches and know about when to flush the cache, when not to flush the cache. If they forget to flush the cache on top of everything else that they need to do, they have a problem, basically, right? So this is really terrible in the end. And in the field, software-based cache coherence have been proven to be not so great in general. For example, I will mention the IBM cell processor. Maybe I'll mention it right now. These cell processors, it's in Sony PlayStations, right? And these folks basically decided in 2000s that they don't want to have hardware cache coherence because it complicates our hardware. Let the programmer and the compiler enforce cache coherence at the software level. And they figured out that this was a disaster to program for programmers. So if you've seen anyone who's programmed an IBM cell processor, they would tell you that, including the architects who designed the processor. Basically, they said this was a bad idea in general. So have some sort of hardware cache coherence in your processor if you want to make it easier to program. So basically, we're going to talk about hardware cache coherence because of that. It greatly simplifies the software's job. And one very basic idea is very similar to this flush global A, but it's done in hardware level. So hardware guarantees things. So the idea is to invalidate all other copies of block A when a core writes to A. Okay, any questions? I'm going to show that protocol next. So this is our simplest protocol, basically. It's a very simple coherence scheme. It's called valid-invalid protocol, let's say. I just made up VI protocol. And caches snoop or observe each other's write and read operations. If a processor writes to a block, all others invalidate the block. That's the idea. So this requires a state machine for a given block. So this is the block's perspective. The block can be valid or invalid in any cache. When a processor wants to read a block, well, let's say initially it's invalid. When a processor wants to read a block, it basically sends a bus read request and goes to a valid state. When a processor wants to write to a block, it sends a bus write request and sends that bus write request to everyone. And it also goes to an invalid state. So in this case, we're assuming actually a particular cache. It's write through and no write allocate. Whenever you write to a block, you don't allocate the cache block. And also you actually invalidate in this particular case. You don't invalidate, sorry. No, I explained that wrongly. Let me go back to that in a little bit. But basically, we're going to assume a write through, no write allocate cache, where whenever you write to a cache block, you also write to memory. If the cache block, that's what write through means, right? There's no write back. And no write allocate cache means that whenever you write to a cache block that's not present in your cache, you don't allocate that block in your cache, meaning the block doesn't become valid. Okay, so let's take a look at it. The local processor can take two actions, processor read or processor write, and actions that are can be broadcast on the bus for a given block, bus read and bus write. These are actions coming from different processors. Okay, let's take a look at one example. Let's say the block is not in the cache. The processor, local processor, wants to read the block. It basically reads the block, goes to a valid state, and sends a bus read request on the bus, let's say, and all of the other processors see this bus read request. Now, this bus read request actually is meaningless in this particular protocol. You will, if you study the protocol, you will figure it out, because whenever you receive a bus read request, you don't do anything. You can see that there's no state transition that happens when you receive a bus read request because of the way caches are designed, because of the way the protocol is designed. Now, the interesting thing happens when you write to a block. Let's take a look at this example. You don't have the block in your cache. You write to a block. You send a processor write request to make sure that everybody else invalidates their copy. And you send a processor write request, and the data gets written to memory. And you also this processor write request calls a bus write request on the bus. This makes sure that all of the other processors invalidate their copies if they have a valid copy. So let's take a look at another processor's perspective. If some other processor receives a bus write request, if it is a valid copy, it basically invalidates their block, basically. So that's what happens when you see a bus write request. Then that's the only place where the bus write request takes effect. Because if you're invalid and see a bus write request, it doesn't make sense clearly, right? Because you don't have the block. But if you're valid and you have a bus write request, you invalidate your copy. Hopefully makes sense, right? And then there needs to be, and the key here is the memory is already updated. Whenever you actually write to a block, memory is also updated. So there's no, let's say, dirty or modified state in this particular protocol because we assumed write-through caches. Right? We're going to relax that assumption later on. Let's take a look at this valid state. You have the block in your cache. You want to write to it. In this case, it's a write-through cache. You write to memory, and you also send a bus write request so that anybody who has the block valid invalidates it. So what happens after this happens, if you have the block valid and you send a bus write request, this processor is the only processor that has the block at the end, and also memory has the same copy. Right? So this is the write-through cache. If you have the block valid in your cache, and if you want to do a read request, then you don't need to tell anyone. You just read the block, because the protocol ensures that valid state means that the data that you have is up to date, and memory also has the data. And there might be other processors who have the data also, but you don't care about them, right? Because everybody has the same copy. So basically, there needs to be some invariants that are imposed by the protocol. So valid state in this case means that essentially it's a state where you have the data, memory has the data, and maybe some other processor has the data, but you don't know about that. And all of the data is consistent, basically. It's not modified. That's the meaning of the valid state, and that's the invariant. Invalid means you don't have the data, clearly. That's it. That's a very simple protocol. You can guarantee its correctness, etc. You can formally prove it, which we're not going to go into, but these are important things to do, actually, to make sure that this works in an implementation also. Okay, this was simple, hopefully. We spent some time because we're going to build on this protocol to actually make the protocol more complicated as time goes on. So, yes. Yeah. Yeah. Yeah, I mean, in this particular case, it doesn't it doesn't help, right? So it doesn't need to send the bus tree. That's what I mentioned earlier, right? In this particular case, it's useless. But it'll be useful for later protocols. That's why I wanted to keep it over here, so that you're kind of accustomed to it. Okay, so before we go into more complicated protocols, let's talk about these non-solutions. I will assume that these are non-solutions. If you don't have hardware as coherence, as we discussed, this is microarchitect's life is easier, but average programmers and even sophisticated programmers' life becomes much harder. Now, we already discussed this basically, and then you have a lot of overhead also. Even if you are a very smart programmer, you cannot get around the overhead issue because you need to do page protection, page-based software incoherence, maybe use non-cacheable operations. All of these are basically very heavy-handed things. again, as I mentioned, all caches may be shared between all processors. You can assume that. Clearly, there's no need for coherence, so we shouldn't be having this lecture if this was the case, but this is impossible to do essentially, especially in large-scale systems, because shared cache becomes a bottleneck and very hard to design a scalable system with low latency cache access this way, essentially. That's why we have a cache hierarchy, right? There are private caches in between levels. L1 cache is private. You have instruction and data. L2 caches are private in many systems today, actually. Yeah. Okay, so essentially, if you want to maintain coherence, you need to guarantee that all processors see a consistent value. In other words, consistent updates for the same memory location. So writes to a location A by processor 0 should be seen by processor 1 eventually. Eventually is important also. And all writes to A should appear in some order. So this requires two properties, essentially. You need to propagate the writes. Writes are also called updates. I'll use them interchangeably. You need to guarantee that all updates will eventually propagate. And you need to serialize the writes from the perspective of that location, right? Provide a consistent order seen by all processors for that same memory location. And this is required for coherence, essentially. If there are any questions on YouTube or somewhere, let me know. I don't see it. Okay, so for this, you need a global point of serialization per memory location. And in this case, I say per memory location, but we're going to talk about cache blocks. Just like in prefetching, we said prefetching is done at the cache block granularity. Coherence is also enforced in cache block granularity today, because again, the problem is really with cache. But you can go to finer granularity, do it at the word level or bit level, but that becomes very, very expensive in terms of hardware overheads. So I've already given you the basic idea, but basically, if you want hardware cache coherence, yes, you have a question? Okay. Okay. That's essentially a cache block, cache line. It's the same, 64 bytes, let's say. I mean, in the program, you have no notion of cache blocks in the program, right? In the program, you have no notion of objects, and they may map to the same cache block, different cache block, depending on the size of the object, depending on where they're located. Well, it's basically, if you go back to this, you want to get the correct value, right? So for example, this could be a variable. It could be 4 bytes. You want that 4-byte value to be correct. So if somebody updates that 4-byte value to be 2000, you should get that update, right? It's the data value. It's the value stored in the cache block. That's true. Essentially, updates to the memory location. I don't know where. Maybe in this slide you have basically see a consistent value for the same memory location, right? It's really about the value in the memory location. Mm-hmm. Mm-hmm. Exactly, yes, exactly. So a page is at the virtual memory level, right? Mm-hmm. It is still mapped to the, it can still be mapped to the physical memory location, right? Yeah. You can think of it that way, yes. Okay. So it's all about the data values in a given memory location in the end. I don't care where the memory location is, but the problem happens because the same memory location, same memory address get cached in different places. And it may take different values in different places because not everybody sees the same updates. And we want to make sure that everybody sees the same updates. Exactly. That cache block, a cache line or cache block, it's the same terminology, that houses that value that's written to that memory location. Yeah. Because cache line may be larger than the update granularity that you have, right? Yes, you have it.
Because the program is setting a variable, but when you perform an access, is a cache needs to go to the memory of cache block.
Okay. Well, I think yeah, I mean, certainly virtual memory gets translated physical, right? But in the end, it's a memory, you have a memory location that you're updating. And that is what matters, right? That memory location gets cached in multiple different caches, and you should get the same value if one of them updates the location, right? So in the end, it's maybe ignore all of that complexity. It's really fundamentally about a given data value that you're updating. What value should you get, right? That belongs to the same memory location, and one processor updates it, and the other processor also reads it. Who should get the value? So I can ignore that complexity of virtual memory. Yes, virtual memory changes things, but it doesn't change the fundamentals of cache coherence. Maybe what threw you off is really this page level coherence, but then you need to think about that in more detail. I didn't cover it in more detail. Okay. Okay, where were we? Okay, here. Basically, the basic idea of hardware cache coherence is a processor or cache. I'm going to use also those kind of interchangeably because we're going to assume kind of processor and cache are coupled in this particular case. Broadcasts its write or update to a memory location to all other processors. And another cache that has the location either updates or invalidates its copy. So it's basically simple. And this immediately gets us to two different kind of protocols, right? Update-based versus invalidate-based or hybrid. So whenever a processor broadcasts that I'm going to update this memory location, should everybody else invalidate the same memory location if they have it in their caches? Or should they update the data? Update the data requires that the processor also send the data that it's using to update the memory location with, the new value basically, and also everybody latching that data in their caches, right? Okay, so this is basically update versus invalidate. How can we safely update replicated data, right? So there are two protocols. One is update protocol, push and update to all of the copies that you have in all caches. And the second one is invalidation, essentially, like we discussed earlier. Ensure there's only one copy, local, and update that copy. Hopefully both make sense, right? So let's take a look at it. On a read, if a local copy is invalid, you put out a request. If another node has a copy, it returns the data value. Otherwise, the memory does, clearly. Another node, in this case, another cache, right? On a write, you read the block into the cache, just as before. Now, update protocol and invalidate protocol differ over here. Right? Update protocol, you write to the block and simultaneously broadcast the data value and the address to all of the other caches. And the caches that have the block update their values. Makes sense, hopefully, right? If you basically check whether you have the memory location, and if the memory location or if the cache block is already valid in your cache, now we will see it maybe in a different state, you basically get the data and update it. Okay? So invalidate protocol, essentially you don't send the data, you write to the block and simultaneously broadcast invalidation request. So you don't send a 64-byte cache block, let's say, or the delta update that you're doing, a small amount of that cache block. You just send the address of the cache block that you're writing to and say invalidate if you have the copy. And other nodes invalidate the block, other caches invalidate the block if the block is present in the cache. Hopefully that makes sense also. So the question, of course, immediately becomes which one's better? And people have actually looked at this a lot. In this case, basically, which one's better depends in the end. Like many questions that we ask in this course, it depends. It really depends on what happens to the behavior of basically what happens to the cache block you're updating, how frequently you're writing, and who's sharing it. So, for example, update protocol is usually good if the share set is constant. There's a constant set of shares, and updates are not very frequent. So, for example, if you have one processor writing to a cache block, and then it's not going to change that cache block, but another processor needs that value immediately. Now that's good to update that processor, right? Because no one is going to update that block before that value that you wrote to that block is read. So that kind of pattern is useful for update protocols. But if there's a lot of writing to the cache block before anyone reads it, this update protocols become very inefficient because you send all of the updates to everyone, but then nobody uses those updates. And eventually someone reads, and then at that point, the update is used, right? Does that make sense? So basically, that read-write behavior is really important. For example, this is what I mentioned, basically. If data is rewritten without intervening reads by other cores, updates essentially are useless, right? So in general, modern machines don't use update protocols because of this reason. Because if you actually send the data to some other cache and then they update it, usually that's a lot of overhead, first of all. That's a lot of bandwidth overhead on the shared bus. And also the other processor may not use it unless you have some other information like sharing information. Though, so people have proposed a lot of research mechanisms where if you actually can guess which processor is going to read a location that you're writing to, you can actually update only that processor, for example. Now you can basically become smarter in your coherence mechanisms, right? You don't update everyone, but basically you speculatively guess which processor is going to get this update that you're doing and update that processor. But again, this may be very difficult because this may be difficult to predict because imagine many processors working on a lock. So a lock is a data structure, is a synchronization metadata that gets updated once in a while, clearly, right? Whenever you release the lock, for example, you update the lock. And when you release the lock, let's say you're writing to the shared data, and what happens is you're updating it in your cache. And the question is, do you send an invalidation to all of the other processors, or do you send an update saying that basically changing the lock location? Now, you could argue both potentially, depending on the synchronization pattern, right? Only one of the other processors perhaps will get the lock in the end. Okay, so this is something to think about, basically. It depends also on what kind of data that we're talking about, right? Is it a lock or is it a shared data structure? What is the frequency of updates to the lock? What is the frequency update of the data structure? And in general, I would say, is it synchronization metadata or is it real data that you're updating? Lock is not the only synchronization primitive, as we discussed. Right? Okay, so one of the, as I also mentioned, one of the other problems with update-based protocols, essentially this creates a write-through cache policy. Whenever you're writing, you're really writing to writing out of your cache, and all of the other processors are reading it. Here, the bus can become a bottleneck. So for these reasons, update-based protocols are not preferred. Invalidate-based protocols are simpler. After invalidation, whenever you basically invalidate all of the other cores cache blocks belonging to the same memory location, the core that invalidated everyone else has exclusive rights to that block. Basically, you can exclusively update it because you know that you're the only core that has the block. And only cores that keep reading after each write retain a copy. So that write happens, and then some other core reads, so it has to get the value. That value needs to get transferred from the cache or from memory. But of course, the downside is if write contention is high, this leads to ping-ponging. What this means is basically whenever a processor writes to a block, it invalidates everyone else. And then another processor wants to write to the block, it invalidates everyone else. Basically, there's a lot of invalidation traffic that happens, and someone needs to reacquire the permission to update the block. So write contention, and write contention is not necessarily the worst case in this particular case, but if you're doing a lot of writes and reads, for example, you may need to have a lot of invalidation and reacquire traffic. So this is called ping-ponging, basically. And ping-ponging is essentially, let's see. I think I'm going to turn this off, and I need to do something here. Okay, so how do we change it? FaceTime, change it to FaceTime. I mean, this camera. Yeah, I prefer not to do that. Let's not do it here. Let's just use the FaceTime camera. It'll be okay? Because that GoPro has always problems. Now just tell me if you can see it. So I'll stop sharing. Okay, that looks not too bad on my end. Okay, if it's okay, yeah, I'll just stick to, it's not going to take too long. We can fix it in the break. So basically, you have processor 1, let's say processor 2. And just to make it more dramatic, you have processor 1000, let's say, right? And then each of them have caches clearly. That's why processors and caches are like this. But basically, this processor is, let's say, it wants to write to this block. At this point, it sends an invalidation request to all of them, right? So everybody gets invalidated. And then another processor reads that block. And maybe multiple other processors read that block. Assume that this is a lock, right? And let's say 900 processors read that block, and they get the updated value after they're invalidated. So they have the value. Now, one of them wants to write to that block. Let's say this one over here. It invalidates everyone else. So now what happened is this cache block was written by this processor, invalidated everywhere else. Everybody else reacquired the cache block using a read with some latency. And then one other processor wrote to that block, and then everybody else got invalidated again. So this is the ping-ponging approach. Why is it ping-ponging? Basically, this cache block gets ping-ponged like a ball from this cache to this cache. And then maybe the same thing happens. And this after this processor finishes its write, after everybody's invalidated, some other processors read the same cache block. And then this processor decides to write to it. It invalidates everyone else, and the cache block gets ping-ponged over here. And then you keep ping-ponging the cache block across many different caches. So this is the problem with caching and synchronization in general. So this could be a lock, for example, a very heavily contended lock that gets ping-ponged across many, many processors. And the problem with the invalidation-based approach, actually also with the update-based approaches, you basically have a lot of invalidations that happen. Essentially, a lot of the reads that you've done are useless. But these are actually tough situations to handle for, in general, with coherence. You should really, in general, you should try to avoid this at the programming level, if possible. So with higher level synchronization constructs, you can try to avoid this, because this probably is happening because a lot of processors are trying to contend for the lock very quickly. And as a result, locks get cached in all of the processors, and then one of them is acquiring the lock and everybody gets invalidated. If you use an update-based protocol, everybody gets updated. Essentially, this is very hard to avoid. Now, invalidation-based protocol is worse in this particular case because if you update everyone, you don't need to have another read request, right? So what happened with invalidation-based protocol is somebody does a write. We are going to call it read exclusive also. You get a lot of invalidations everywhere. And then a lot of reads from different processors happen. And then somebody else does a write, and then you get a lot of invalidations, and then it basically continues like this. But this is an invalidate-based. Oh, am I out of the? Okay, how about now? Yeah, this is the downside of this picture, actually. This is invalidation-based protocols, right? Whereas update-based protocols, you don't have at least some of the overheads. So you do a write, magically updates also happen. No invalidations. Somebody does a read, no problem, because they got the updated value. And somebody else does a write. Again, lots of updates happen. And somebody else does a read, no problem. Again, basically, you get rid of the invalidations over here. And if invalidations are causing a lot of ping-ponging, update-based protocol may be better in that particular case, right? So even then, it's not that great because you send a lot of updates over here, right? So there's energy overhead for these updates and maybe latency overheads also. Yes. Because again, it can be a contended. This data location may be a contended lock, right? Lots of processors are trying to get the lock. They're doing some reading for the lock, and then they're going to test the lock, and then they're going to update the lock. No, lock is this is the lock that we discussed in earlier lectures. This is a lock to protect the shared data. It's a synchronization construct. Okay. Yes. Yeah, I mean, it depends basically. It depends on the design. We'll talk about interconnects tomorrow. If it's a bus-based design, like if you have, let's say, 4 or 16 processors, it should be similar. Invalidation should be similar to the update, but update has a lot of overhead and it requires basically communicating the data all over the place. But if it's an interconnect, if it's a huge system like 10,000 node system, invalidation requests may have a special network that you design, whereas it's much more difficult to design a special network for huge blocks like 64 bytes. Invalidation requests are only 1 bit, let's say, maybe some metadata. Well, you need the address also, sure. But the address is much smaller than the 64-byte cache block, right? So basically, that's why interconnects comes next. Interconnects actually enable the scalability in the end, and update-based protocols become a little bit more difficult with when you get to like thousands of machines. Okay, so hopefully that was visible. Now we're going to go back. Yes, go ahead. Two locks and I mean potentially, yeah. I mean, again, you can imagine many issues over here, right? If you have two locks and they're different locks and different processors are actually updating it at different times. Now what happens is you have the same cache line housing two completely different locks. This issue is called false sharing, basically. Even though the lock may not be needed, one lock may not be needed by one processor, but the other lock may be needed. You get coherence invalidations because some other processor is reading the other lock that you don't need. And this issue is called false sharing. And false sharing happens because the granularity of coherence is larger than the granularity of updates, right? The granularity of coherence, in this case, cache block granularity, 64 bytes. Your update may be only 4 bytes, right? Any other processor that touches any other of the 60 bytes is going to invalidate your cache block or update it, depending on the protocol. So this is the issue of false sharing. That's a very good point, basically. We were going to talk about that later on, but it's good that you brought it up. Okay, so let me go back here. How do I do that? Okay, this one. Okay, so I mean, you can see that there are a lot of issues that affect the software and hardware stack over here. But again, fundamentally, we're going to talk about how does the hardware support the protocol that we will discuss. Okay, let's go to the next slide. So we're going to discuss actually two cache coherent methods. And they're going to both answer the question, how do we ensure that the proper caches are updated? Snoopy Bus Protocol, it was developed by these two major papers. I assigned the second one as a reading. It's actually very clean and nice. You can take a look at it. Basically, this is bus-based. It's assuming some sort of bus. And it's a single point of serialization for all memory requests. And that's essentially the bus. Processors observe each other's actions on the bus. For example, processor 1 makes a read exclusive request for address A on the bus, and processor 0 sees this and invalidates its own copy of A. Read exclusive means that I'm going to write to this cache block. It's usually called read exclusive because I want to get the cache block exclusively for myself. That's why it's called read exclusive. Directory-based protocols are actually older, but essentially more scalable. They enable scalability. This basically here you still have a single point of serialization, but it's per block. It's not a single point of physical serialization like a bus. Everybody sees all of the accesses. It's really a per block single point of serialization. It could be distributed among the processors, and this is why it's scalable. Basically, every block has a home node, and whenever you want to actually access that block, you need to send a request to the directory saying that directory, I want access to this block. And the directory knows everything about that block, which processors have it, which processors don't have it, and which processors have written to it, for example. So basically, I've said this, processors make explicit requests for blocks from the home node for a given block. And the directory tracks which caches have each block. And the directory coordinates invalidations and updates. So basically, you introduce an indirection. Here, there is no indirection in the Snoopy bus. You broadcast an invalidation or whatever you're doing, and everybody sees it. Here, you send a message to the directory, update the directory, and everybody consults the directory before taking any action on a memory location. So for example, processor 1, the same read exclusive request goes like this in directory-based protocols. Processor 1 asks directory for an exclusive copy, sending a message to the directory. Directory gets the message and asks processor 0 to invalidate, assuming the processor 0 has the value cached. It waits for an acknowledgement and then responds to processor 1. So you can see that there's a lot of message exchanged. Okay, so let's start with directory-based cache coherence because I think this is actually simpler to think about, if you will. You have a central coordinator for a given block. And again, I said the idea, but you have a logically central directory. Logically, this is centralized. It keeps track of where the copies of each cache block resides. And caches consult this directory to ensure coherence. But physically, the directory can be distributed. It could be actually anywhere. I mean, it doesn't have to be in the memory side, but usually it's implemented in the memory controller, but it could really be anywhere if you think about it. So an example mechanism is that like this. For each, a very simple one, for each cache block in memory, you store p plus 1 bits. P is the number of processors or caches. As I said, processors and caches are the same in this particular case. You have 1 bit for each cache, indicating whether the block is in the cache. So this is, remember, for each cache block, for cache block A, B, and then A plus 1, A plus 2, A plus 3, these are cache block addresses. So you have 1 bit for each cache, indicating whether the block is in that cache. And then you have an exclusive bit, which is the plus 1 bit, that indicates that a cache has the only copy of the block and can update it without notifying others. So this is this could be useful, as we will see later on. So exclusive bits tells the directory that this is the cache that has the only copy. You don't necessarily need it at the directory, but I like having it because mentally it says that, okay, the block is exclusive. There's no other cache other than this particular one that has the bit set. One of the p bit set has the block. Now on a read, what you do is you set the cache's bit, one of the p bits, saying that this cache will have the data in its cache. And then the directory arranges the supply of data. Now, what does this mean? As I said, directory knows everything about where the block is. It could be in memory. If it's in memory, if the up-to-date copy is in memory, the directory sends the copy from memory to that cache. Or the directory knows that cache 456 has this block. The directory says, cache 456, send the cache block to cache 45, who's requesting it from me right now. So the directory is the coordinator, basically. It can basically send messages to different parts of the system and send the data, and essentially arrange the supply of the data. Right? And once it gets all the acknowledgements saying that this is done, it sets the necessary bits. So on the right, what the directory does is it basically knows which caches have the block, and it invalidates all caches that have the block and resets their bits. How does it do that? Basically, it knows this p bits over here tell the directory which caches have the block. So it basically says cache 5, cache 25, cache 565, cache 10,455. They all receive invalidation requests and they invalidate their blocks. Again, they could receive an update request, right? This protocol is different from, so update versus invalidate is a choice that could be combined with directory-based cache coherence or bus-based cache coherence, as we will see. Okay, so, but this is not enough because you also need to modify the caches a little bit in this case, if you want to have this exclusive access. You need to basically, because what does exclusive mean? Exclusive means that this cache has the block and no one else has it. So it can do updates without notifying anyone, including the directory. That's the beauty of exclusive. Basically, you basically don't need to tell anyone whether you're updating the block. But of course, for this to work, you need to know that you have exclusive access to the block. How do you know that you have exclusive access to the block? You have to have an exclusive bit in your cache saying that you're the only one who has the block. And the directory needs to tell you that you're the only one who has the block. Does that make sense? So this requires some modification to the caches. The beauty of cache coherence, the directory-based cache coherence is normally it should not require any modification to the caches, but if you want to optimize for this exclusive access, you need to modify your cache such that each block has an exclusive bit. If that exclusive bit is set, the cache basically checks the exclusive bit and says, I'm going to do a write. I just do my write and not notify anyone, including the directory, because the directory gave me the permission that I could exclusively update it, because it has ensured that no one else is going to touch this cache block while I have my exclusive bit set in my cache. That's the idea. And this is very powerful, as we will see. We're going to add that exclusive bit into our protocols later on in the bus-based systems as well. So I think this is a pictorial. I wanted to update these slides, but I didn't have any time, but it's still readable, I think. But basically, you can see that this is an example directory-based scheme where P is 4 and you have an exclusive bit. And essentially, this is for a given cache block. For every cache block, you need to have this. So we're going to talk about the cost of the directory-based schemes later on. So P is 4 in this case, so you have only 5 bits, as you can see. That's not bad for a cache block. So all of the bits set to 0 means that no cache has the block, and directory has this information. Right? Now let's say processor 1 takes a read miss to block A. What the directory does is directory checks no one has the block. So processor 1, you can take the block, and directory supplies the data from memory to processor 1's cache, and then sets the bit vector to indicate that processor 1 has the block. This is 0, 1, 2, 3, as you can see. And then processor 3 takes a read miss, notifies the directory, says, directory, I want this cache block. Can you give it to me? The processor says, no problem. It basically says, supplies the data either from memory or tells processor 1 to give the data to processor 3, depending on the network structure, as we will see tomorrow. It then sets processor 3's bit. Now, both of the processors have the cache block, right? And the directory knows that. So it's basically a simple bit vector-based scheme. Now, the interesting thing happens when the processor 2 takes a write miss. So this is the state. So processor 2 says, I want exclusive access to this block. Let's assume that that's what write miss means. And notifies the directory. And then directory looks at the bit vector, says, 2 of the caches have the block. I'm going to first ask them to invalidate their blocks. It will basically ask processor 1 and processor 3 to invalidate their blocks. And then the bit vector will become all zeros. And then after receiving acknowledgement saying that we have invalidated our blocks, you can move on directory. And the directory basically says, okay, it also, of course, has the data because nobody was exclusive, as you can see. So it basically supplies the data to processor 2 and then sets processor 2's bit to 1. And then it knows that processor 2 is going to write to it. So it basically sets processor 2 bit, the exclusive bit to 1. So this basically says processor 2 has the data in exclusive mode. And now after this point, processor 2 can update the block without notifying any other processor or the directory, because this is granted, this block is exclusively granted to processor 2 as the directory state shows. Makes sense, hopefully. So, okay, basically you need to get the directory right, you need to get the messages right in this particular case. And then let's say processor 3 takes a write miss. What happens at this point is, I said memory controller here because I'm assuming directory is in the memory controller, but directory essentially requests the block from processor 2. So that's another interesting case, right? Processor 2 has the block right now. The directory receives a message from processor 3 saying that processor 3 wants to write to this block. The directory says, oh, processor 2 has an updated copy of block. I'd better get it first. And basically notifies processor 2. Processor 2, invalidate what you have and give me what you have. And the processor 2 obeys, sends the data back. And the directory gives the block to processor 3, sends it to processor 3, and says, processor 3, now you have exclusive access. Sets its bit and sets the exclusive bit. So basically, it's simple once you know what these bits mean. And then if processor 2 takes a read miss, that's also another interesting case. Processor 3 has the block exclusive. Processor 2 takes a read miss. You can imagine what happens basically, right? At this point, the directory says processor 3 has the up-to-date data. Now let me actually get the data from them or ask them to send the data to processor 2 and get their exclusive access back, because now they're going to share the data between processor 2 and processor 3 and sets the bits accordingly. This is not the only action you can take, right? Maybe there's some other optimization you can do depending on the access patterns, but this is the baseline directory scheme. Hopefully that makes sense, right? And you can study it. It's not magic, let's say. Okay, no questions? All makes sense? Yes. Mm-hmm. Can you use the Yeah, absolutely. You need to remove the block from that processor's cache. That has to become invalid. That's what invalidate means. Yeah. Absolutely, yes. Yeah. Basically, that's what invalidate. Whenever the directory sends a message, invalidate this cache block from your cache, the cache has to invalidate it. If that doesn't get done, then this doesn't work, right? Yes. Yeah. Now you're thinking deeply. But right now we're just considering just one cache, right? But yes, if the value is somewhere else also replicated, this has to happen everywhere, right? Basically, whenever you replicate data, you have to make sure that that data is coherent. Otherwise, you have a problem, right? But yes, absolutely. Basically, you cannot cheat in a sense. You cannot buffer the data somewhere and say, oh, I access it privately. No, if you don't basically keep things coherent, you're going to run into problems. That's a good point. Okay, so basically here directory is the coordinator, right? We said this is a level of indirection, right? And this indirection enables scalability, but enables latency. It adds latency also. Now, this is really the coordinator for all actions to be performed on a given block by any processor. It guarantees correctness and ordering. Yet there are many opportunities for optimization. So these are enabled by bypassing the directory and directly communicating between the caches. And we will see examples of these optimizations later. Because directory knows this information, it may also know the topology information, right? Which caches, which processors close to each other. Basically, the directory may be coordinating accesses across 1 million processors, right? And it could be a cluster, right? And it should be a shared memory cluster. And the directory knows the topology of this cluster, how close the processors are to each other. And based on that topology information and the latency information, it can say, I'm not going to send the data to this processor, even though I have the updated copy, but I know that some other cache over there has the data, and it's much closer to this processor. So I'm going to tell that cache to send the data to that processor. So it can basically do this sort of optimizations because you have the global picture. This global picture is very useful. With bus-based, Snoopy-based protocols, you don't have this global picture because you're just broadcasting and everybody is basically observing what's happening and they're doing something, right? There's no coordination in the sense that there is no intelligence that you can embed into that coordination. And you could, of course, try to get the best of both worlds, and we may talk about them, but let's talk about Snoopy cache coherence first. Okay, so that was directory. Let's talk about Snoopy cache coherence, and then we'll probably take a break. Going a bit slower than expected. Okay, so I've already given you this idea. Essentially, all caches snoop all other caches, read write requests, and keep the cache block coherent. Each cache block has some coherence metadata associated with it in the tag store of each cache. So directory has all the metadata. Here, we're going to put coherence metadata into the caches, as we will see. So this is easy to implement if all caches share a common bus. Everybody sees everybody's updates, essentially, or broadcasts. Each cache broadcasts its read-write operations on the bus. And this is good for small-scale multiprocessors. We're going to discuss this tomorrow. Essentially, a single bus becomes very contended if you actually start adding 16, 32, 64 processors to it. And it becomes very difficult to scale this, essentially. Yeah, and then the question is, what if you want to have a 1 million node multiprocessor? So this doesn't scale, basically. Then you need to create a virtual bus on top of a non-physical bus interconnect. Basically, underneath, you may have a distributed interconnect. But if you want Snoopy cache coherence, meaning you want to do broadcast across that distributed interconnect, now you don't have the physical single point of serialization. You need to guarantee it virtually, and it becomes a huge mess, basically. I'm not going to go into that. It is possible, but it's very, very expensive and, let's say, dangerous, because there are many, many corner cases that you need to consider now, because your physical medium doesn't allow the broadcast to be seen by everyone, let's say, easily. Okay, so I'm going to use some examples that are similar to what we have looked at before, but basically this is what we're going to assume, right? You have processor 1, cache 1, there's some coherence metadata in each caches, and then there's a shared bus, and then there's a memory over here. As I said, each cache observes its own processor and the bus, and changes to the state of the cache block is based on the observed actions by processor and the bus. So let's say the actions are going to be very similar. Processor is going to do either read or write to the block. And the bus actions to a block coming from another processor that you observe will be bus read and bus write. Bus write is also called bus read exclusive, as we have discussed, right? So we've already seen this protocol. Basically, this write valid invalid protocol that we discussed essentially assumes something like this. You could also implement it. So I should also mention that this protocol can be implemented in the directory level also, actually. The protocol that we are going to discuss, like MESI, etc., can be implemented at the directory level. But what we discussed earlier was based on a bus base because we were assuming these signals, right? If you want to implement this in a directory level, you need to basically convert these signals to directory requests, essentially. So the protocols we will see are actually at a higher level than whether they will be implemented in a Snoopy bus or directory. But now let's take a look at this protocol. This was valid invalid. And what if you want write back caches? It becomes a quick question, right? We assumed write through over there, but we know that write through is not that great because it has a lot of overhead in terms of bandwidth. I want write back caches. Now you want a modified state or dirty state, essentially. Now you need to extend the protocol. So how do you extend the protocol? So now you have 3 states. You have metadata to encode to these states per each block that you house in the cache. Modified means cache line is the only cached copy and it's dirty. Shared means cache line is one of potentially several cache copies and it's clean, meaning at least one clean cached copy is there in the system. Invalid means cache line is not present in this cache. So that's the semantics or invariance of these states, the definition of these states. Now, if you take a read miss, you send a read request on the bus and the processor immediately transitions to a shared state. We're going to see that this is a problem later on, but assume that that's the case. And then the processor gets a write miss and it makes a read exclusive request and transitions to the M state. And when a processor snoops read exclusive request from another, basically if it sees a bus write or a bus read exclusive request, it must invalidate its own copy. So basically in the modified state, the cache line is dirty, and so there's only one copy. This is what is guaranteed, right? Well, okay, now if you want to go from shared to modified, so if you have the block as shared and you want to write to that block in your cache, you can actually just keep sending invalidations to everyone. You don't need to access memory because you have the data in your cache. You just invalidate everybody else's copy. So this is the state machine. This is from the Color and Sing book that I mentioned earlier, Parallel Computer Architecture. But you can see that we've extended, and the interesting parts are here. For example, if you're in shared state, you have the data, you write to a block, you send invalidation request, bus read exclusive request to everyone, and then you transition to the modified state, you have the copy at that point. Now, if somebody, if you're in invalid state and you want to do write, you again go to modified state immediately and send a bus read exclusive request to everyone. Now, everyone who receives a bus read exclusive request, they flush their cache if they're in modified state, for example. Also in shared state, if you're in shared state and if you get a bus read exclusive request, then you don't need to do anything because the data that you have is not valuable to anyone because the data is present somewhere else. So you go to the invalid state. So I should have marked this over here. Let me try to do that. Oh, okay. Maybe I should not try to do that right now. No, I will. So these are also interesting states if you want to follow it, basically. No, that's not what I want. I want to share, right? Okay, better. Okay. So you can go through this on your own, but you can also see that when you're in modified state and when you do a write to the block that's in your cache, because of the semantics of the modified state, you don't need to tell anyone, right? Because you're in modified state and you know that no one else has the copy in this particular case. Okay. Any questions? Yes. Yeah. Yeah. I mean, there is basically a bus arbitration that happens. Only one of them will win the bus. And the first one that gets the bus will invalidate everyone, basically. Yeah. But this becomes more difficult when you start pipelining the bus, etc. But yes, you need to have some ordering. But in the end, you have the ordering in the bus. A single bus helps that ordering. So there are some race conditions that you need to deal with, even when you have a bus, actually. That's why, as we mentioned in last class, a lot of the bugs that happen in real processors are due to coherence or memory ordering. Because these are not easy things to get right, especially if you have a very high frequency, high speed pipeline bus implementation. Even if you have a bus. Assume that you start with a bus even. But normally we don't even have a bus today. Well, we have a bus, but we have other stuff, other interconnects as well. And our shared memory region is bigger than just the domain of a bus today. Okay, so there's a problem with MSI, and people have discovered that. Essentially, if you have a block that's in no cache to begin with, what happens is you read the block, and the block immediately goes to the shared state, even though this may be the only copy that's cached in the entire system. And then maybe no other processor will cache it. So why do you go to the shared state? Because if you go to the shared state, you need to get another permission to update that block. Right? That's the problem, basically. Well, why is the problem? Essentially, suppose the cache that reads the block wants to write to it at some point. You read the block, and at some point you want to write to it. It needs to broadcast invalidate requests, even though it has the only cache copy. It needs to broadcast invalidate requests because it doesn't know that it has the only cache copy. It has to do invalidations. But if the cache knew it had the only cached copy in the system, it could have written to the block without notifying anyone else, essentially. This saves unnecessary broadcast of invalidations. And essentially, the problem is here, right? You don't have the block. You get a read. You read the block. You go into the shared state. And then when you want to write to that block, you send a lot of invalidations and then go to the modified state. Here you have the block exclusively to yourself. Not necessarily, as we will see, but you can update the block essentially. And then basically you can do the updates. But basically this, if you are going to actually at some point write to this block, why not actually go to an exclusive state that's separate from the shared state? That's the idea over here. So the solution is essentially messy, which is add another state indicating that this is the only cached copy and it's clean. So, okay, maybe I should say that this is exclusive, but it's modified. But we're going to add another state that says this is the only cached copy in the system and it's clean, and you have exclusive access to this block. So you can write to it without notifying anyone. This is called the exclusive state. Unfortunately, it's not, exclusive state is not specific enough. There's two exclusive states, exclusive clean and exclusive modified. Both are exclusive states in the end. Yes. Mm-hmm. Yeah, this one. When it's modified and there's a bus read, we're going to talk about that, I think. Because, okay, why does it go to invalid? You're talking about this one? Or you're talking about this one? Okay, so this cache block has it modified. Somebody else is going to write to it. If somebody else is going to write to it, you're going to invalidate what you have, and you're going to supply the data. That's what flush means. Makes sense, right? Because someone else needs to get the data that you have. That's what flush means. You need to flush the data. And then somebody else is going to write to it. So you'd better go back to invalid. Okay. Okay. So basically, we're going to add an exclusive state. The block is placed into the exclusive state if during a bus read, no other cache has it. So you need actually some logic to detect this clearly, right? Basically, during a bus read, now you have to query all the caches, and no other cache should have it. It's expensive, a little bit more expensive, but doable. And essentially, all processors today do it. So essentially, there's a wired or shared signal on the bus that enables determining this. Snooping caches assert the signal if they also have a copy, right? And if they have a copy, then you don't go to the exclusive state, you go to the shared state. If no one has a copy in this wired OR, if the result of the wired OR is 0, meaning basically a cache asserts the bit in the wired OR if it has the copy. If no one has a copy, everyone must have had a 0. In that case, basically, you go into the exclusive state. So now, once you do that, you can have a silent transition from exclusive to modified when you write to a cache block, right? No, you don't need to modify anyone. This is also called the Illinois protocol. It's actually because it was developed in Illinois by Janak Patel and one of his master's students in 1980s, as you can see. And this is a beautiful paper. You can take a look at it. And essentially, I'm going to show that, but I've also shown that earlier. Well, I haven't shown the exclusive part, but I'm not going to go to all of the state transitions. We're going to assume something similar that I've seen earlier. But now we have some more signals to make this work. Basically, we have a bus read, bus write. Bus write is the same as bus write, bus read exclusive. But we have two different types of bus write. I'm going to call them bus invalidate and bus read invalidate. So the first one is invalidate, but you already have the data, so do not supply it. And the other one is invalidate, but also need the data, so supply it. And then we have 4 states. Its M, S, I are essentially the same as what we had earlier. We add this exclusive state, which is essentially exclusive and clean. Hopefully that makes sense also. So this is my picture. We're going to see the Pentium Pro protocol, which is actually very, very similar to this with some differences. But essentially, the interesting parts are here. So if a cache doesn't have the block, and then it does a processor read, and only this processor has the block, only this processor is going to have the block. No one else has it, essentially. The processor transitions to the exclusive clean state because it knows at this point that it is the only processor that has the block. Right? And then it, of course, sends a bus read signal to determine that. Right? Okay, so if you look at this one, maybe we should look at this one first. If the processor doesn't have the block, and it basically has a processor read, it sends a bus read, and basically sees that some other cache asserted the wired or signal, then it goes to the shared clean state. Hopefully that makes sense also. So this is the major difference. You either go to an exclusive state or a shared clean state. Now, in the exclusive clean state, if the processor wants to write to the block, it doesn't send any invalidates, as you can see over here. It just moves to the exclusive modified state. Hopefully that makes sense. These are the interesting, essentially most interesting parts compared to the MSI protocol, which we built up to. And you can see these are highlighted over here. I think I didn't highlight it over here, but I should highlight it anyway. We'll do that later. Okay, this is from the Coherence Sync book. And if you want to do the bonus lab, you will essentially implement something like this. This is beautiful. I'd recommend anyone to do it. This is going to be, as I said, this is going to be one of the hardest labs. I don't think it's that hard, but it will require you to think about it for sure. But it's bonus in the end, right? So the beauty of this course is you can learn a lot without worrying about your grade that much, let's say. Okay, so we haven't released this lab yet, but we will release it. It's going to be very similar to last year's lab, essentially. I'm not going to cover this, but maybe I will just mention some terminology. So a transition from a single owner state, exclusive or modified, are single owner states, if you think about it, right? Exclusive and modified. This is exclusive clean, and this is exclusive modified. It's called a downgrade, basically. Whenever you're transitioning from modified or exclusive to some other state, you're downgrading your permissions. You have fewer permissions on the cache block at that point, right? Because either you're invalid or you're shared, and you cannot write to the block without doing something special. A transition from the shared state to a single owner state, either exclusive or modified, is called an upgrade, because the transition grants the ability to the owner to write to the block, essentially. Okay, and this is the state machine, and you can take a look at it. And this is very similar to Intel Pentium Pro. I'm not going to cover. Essentially, Intel Pentium Pro was one of the first processors that implemented the MESI protocol, and it worked, but it had bugs also. So basically, Coherence protocol is not easy to get right. Now let's talk about some trade-offs in this protocol. So if you go back to this, should a downgrade from modified go to shared or invalid? I kind of assumed something over here. Let's see. Basically, downgrade from modified. So modified, what does downgrade mean? Basically, do you go to invalid, or is there a potential to go to shared when someone else is writing to it, basically? So, for example, you go to shared if data is likely to be reused before it's written to by another processor. You go to invalid if data is not likely to be not reused before it's written by another processor. Essentially, this is again the issue with update versus invalidate-based protocols, right? If you think that the data is going to be reused, maybe you go to shared. If you think that the data is not going to be reused, maybe you go to invalid. And then there's the question of cache-to-cache transfers. I'm going through these relatively quickly because these are optimizations. I'm going to talk about something really important at the end. Basically, cache-to-cache transfer. On a bus read, should the data come from another cache or should it come from memory? This is a similar issue like we discussed with directory-based protocol. Another cache may be faster if the memory is slow or highly contended. So you can think about now, even in a bus-based protocol, getting the data from another cache may be faster because there may be a lot of contention on the memory controller, right? If you get it from memory, it's simpler. There's no need to wait to see if another cache has the data first, and there could be less contention on other caches. But this requires a write back on M downgrade. So what does this mean? Actually, let's talk about this one a little bit. So when you go from modified to shared, if you want to go from modified to shared, you really need to write back the data, right? Since shared state is assumed to be clean, right? That's the semantics of the protocol. Now, this introduces some complication because you need to write back the data to memory. So there's no state where the data is modified and it's shared between different processors, and memory doesn't have the up-to-date copy. That's why you need to write back the results, write back the data to memory. If someone else wants the data, everybody has to basically everybody needs to have the same data, but also memory has the same data. Memory needs to have the same data. So basically, that's the problem. You don't have another state that says the data is shared and modified, but memory is not up to date. Well, modified means that basically shared and modified state doesn't exist. Exclusive modified exists. Exclusive clean exists. But shared and clean exists, but shared and modified doesn't exist. And that's what people realized also. And a lot of these happened by seeing workloads and saying that, oh, This workload, unfortunately, is exercising these write-backs, meaning there are a lot of write-backs happening. How can we fix it? And people introduced this Onur, or one possibility is this basically. It's a Moesi protocol. You may have seen the term Moesi. It's actually implemented in many processors today. Essentially, this is one possibility of fixing the modified to shared downgrade problem with write-backs. Basically, the problem is you may have a lot of write-backs to memory if a lot of processors are going from modified to shared, right? And the issue is really you don't have a state that says modified and shared, right, at the same time. So owner state fixes that problem, basically. It says basically one cache owns the latest data, and memory is not updated. And memory write-back happens when all caches evict their copies. And that owner is responsible for actually updating the memory in the end. So modified to shared doesn't exist because who's responsible for updating the memory? Now you need some coordination, right? So you can, we just realized that modified shared state doesn't exist, but why doesn't it exist? Well, first of all, people didn't think about it, but there's a complication to adding it also, because if you have modified shared, all of the caches have the dirty data. Who's going to write it back, right? You need some coordination over here. So that's why this is called the owner state. Yes. Yeah. Mm-hmm. Exactly. Yes, that's right. So that's a very good point. I mean, yeah, essentially it's a two-state. You need another bit. Well, not necessarily another bit that could be encoded, but you need basically another encoding that specifies owner. That's a very good point. Okay, so basically, I think I've already said this. Observations that shared state requires the data to be clean. In other words, all caches that have the block have the up-to-date copy, and so does the memory. And the problem is so does the memory over here, essentially. And you need to write the block to memory when bus read happens when the block is in modified state. You can decode this after you study it maybe, but basically what I said earlier. So why is the problem? Memory can be updated unnecessarily. Some other processor may want to write to the block again, right, essentially. And this may be a lot, basically, depending on your access pattern. Now your memory gets loaded too much, right? Even though you have the copies and the caches, right? So basically, you're updating the memory unnecessarily. So how do you basically fix the problem? So there actually, Moesi is not the only idea. Moesi complicates the protocol, but actually is powerful. But one way of fixing the problem is do not transition from modified to shared on a bus read, invalidate the copy, and supply the modified block to the requesting processor directly without updating memory. That doesn't require a modified shared state. It still solves the problem, but it introduces some other pattern that's not necessarily good. So that's why a lot of people have implemented the Moesi protocol. You transition from modified to shared, but designate one cache as the owner who will write the block back when it's evicted. But there are basically additional things that you do. This is the basic idea. Now shared means shared and potentially dirty. Now I changed the definition of shared. That's one way of implementing it. Another way of implementing is basically what you said. You added two states as opposed to one state. But this is a version of the Moesi protocol in the end. Makes sense, right? You can either add more states and more optimizations, or you can change the definition of the state. Shared doesn't mean shared, exclusive, shared and clean. Shared means shared and potentially dirty, right? And that's not too bad, actually, in the end. Okay. So basically, in the end, what we're doing right now is we're optimizing the protocol, right? The protocol can be optimized with even more states and more and even prediction mechanisms to reduce unnecessary invalidations and transfers of blocks. However, as we discussed, more states and optimizations are more difficult to design and verify. They lead to more cases to take care of, like race conditions, and they provide diminishing returns over time. So valid invalid to MSI, huge gain. MSI to MESI, a little bit smaller gain. MESI to Moesi, smaller gain, and you start optimizing smaller diminishing returns. You get fewer and fewer gains. And so in some specific workloads, gains could be huge, of course, right? Depending on the access pattern of the workloads. Okay, so I think this is a good place to stop and take a break because we're going to revisit the two cache coherence methods and talk about their trade-offs. So let's take a break for, in this case, I'll do 11 minutes today. Let's come back at 14:55. And then we will continue with the cache coherence methods. No, you need to change the camera. Yeah, I think you need to restart something. Maybe even Zoom. I don't know. Oh. So if you're going to restart Zoom, make sure Mohammed or someone else does that. Do you want to restart it? I think that I don't know how the camera is. Yeah, it doesn't look great. No. We're fine. I'm fine with restarting it. We have time. Okay, shall we get started? Let me remove this thing from here. Is the voice working? Yeah, I think it's good to check once more, and the camera as well. Somehow I lose the thing. Okay. Okay, great. So let's get started. So we're now going to discuss the differences between the two methods, and then we're going to talk about directory optimizations. So Snoopy Bus, we've covered examples of directory. We've covered an example of. As I said, these different protocols, MESI, MOESI, MSI, can be implemented on top of a bus-based single point of serialization for all memory request type of substrate, or directory, basically. These different protocols can be implemented on top of both methods, if you will. But what are the trade-offs? Snoopy Bus or Snoopy cache. Here, the miss latency is very short, right? Whenever you get a cache miss, or whenever you have a coherence request to bus transaction to memory is very quick. You don't need to go through a mediator, which is a directory. Global serialization is easy. Bus provides this already at a physical level. You have the physical arbitration to get the bus. It's simple. You can adapt bus-based uniprocessors easily. You have a uniprocessor that normally has a bus. Now you have a multiprocessor that has a bus, right? Now, unfortunately, it relies on broadcast messages to be seen by all caches in the same order. So a single point of serialization, essentially, for all requests on the bus. And it's not scalable in the end, as we have discussed, right? This is, if you want to go to 10,000 nodes, forget about this sort of thing. So you need a virtual bus. As I said earlier, or a totally ordered interconnect. These are concepts that are harder to implement in a distributed system. And we may mention them tomorrow, but probably not. So directory, I'll start with the disadvantages. Essentially, now you add indirection to the miss latency, right? You basically, whenever you want access to a block, you need to go through the directory. So essentially, this picture over here, request goes to the directory, and then directory gets the data from memory and sends it back. So there's an indirection on the critical path of access. So the latencies are longer with directory-based protocols. It requires extra storage to track share sets, clearly in the directory. Snoopy cache requires extra storage metadata in the caches, right? But we'll compare the two different kinds of storage a little bit. So this directory storage can be approximate, actually. We will discuss this briefly, but you don't need to completely perfectly track who's sharing what, as long as you're conservative. Meaning, you can send extra invalidations to some caches that may not have the data. That's okay. The cache basically sees an invalidation and says, oh, I don't have the data, so I acknowledge it immediately, right? I'm already invalid. What are you asking me, basically? You can actually do that sort of stuff. This is okay for correctness, but of course it adds extra overhead. So basically, by doing approximate tracking of shares, who has the data in what condition, you may be okay. But again, you need to be very careful. Protocols and race conditions are more complex in a directory for high performance, especially when you have a distributed interconnect, as we will see tomorrow. Now, the big advantage of directory is it doesn't require broadcast to all caches. So there's a huge advantage over here. You can implement a protocol without requiring a broadcast, right? And broadcast operation, as I said, is not scalable, right? Operation itself is not scalable. If you want to have a 1,000,000 node processor, and if you want to broadcast things, yeah, it becomes very not scalable in the end. In fact, in some supercomputers, people have specifically designed networks to do this sort of broadcast if they want to have some sort of coherence area where they want to have broadcast-based coherence. So you design a special interconnect to do this broadcast, for example, in some supercomputers. But if you want to have 1,000,000 nodes, does it really make sense to have a broadcast-based invalidation protocol? It's a good idea. Broadcast-based coherence protocol. It's a good idea to consider that. And the other beauty of directories, it's exactly as scalable as the interconnect and directory storage, which turns out to be much more scalable than bus. Even though there's a lot of storage that you need to keep track of, it's still much more scalable because of the interconnect that you have. Now, storage, let's talk about storage. We will see that a little bit. So the storage in the directory is you have to have for every possible cache block that's part of memory that could be cached, you have to keep track of p+1 bits. Right? This is a lot, actually, as we will see. Whereas Snoopy cache is nice in the sense that you don't care what's not in the caches. Right? You only keep track of metadata for blocks that are in the caches. Right? You don't care if something is not in the cache. You don't care, right? Whereas directory has to have zeros for those, right? If nothing is in any cache, directory has a bit vector, which is all zeros essentially, right? So unfortunately, directory uses additional storage. Of course, additional storage to make sure things work. Now, of course, people have developed directories that are cached also. Now this becomes interesting, right? Because you have a directory that the goal is to provide coherence, and you can cache the directory entries also. That makes things more complicated, of course. But we're not going to talk about that because you need to keep that coherent also, right? So keep that in mind. This is kind of like you have to have, anyway, I'm not going to go into that, okay? In virtual memory, for example, you have page tables, right? And then you don't, page tables can itself, they themselves can reside in virtual memory, right? It's kind of like that. You're providing this directory to keep track of what's inside the caches, but the directory itself can be cached. So it has the cache coherence problem itself, right? So basically you need to be careful about these things. Okay, so let's revisit directory-based cache coherence. We've already discussed all of this. I've already given you examples. But basically, these protocols are employed in all systems today, all large-scale systems. It's usually a combination of bus-based cache coherence and directory-based cache coherence in today's systems. But you need to go to directories when you need to scale past the capacity of a single bus. It's fundamentally distributed. Coherence still requires a single point of serialization for a given block. It should be a given block. What happened to it? I guess I don't know how to spell. That's what happened to it. It's still shared, right? But I cannot now find the thing. Oh, it's lost. Where am I? I cannot find the pointer, but maybe it's over there. How do I go down? Okay, yeah, there it is. Much better. These multiple screens. It goes up very quickly. It's very sensitive. Okay, thanks. Okay, basically, you still need to have a single point of serialization in the directory. Okay. But that single point of serialization can be different for different blocks, essentially. So you can basically stripe it across nodes and memory controllers. So basically, I guess very quickly, I don't know why this is up here. Okay. Oh. Something is happening or not happening. Stop share. Okay, this is better, I guess. So basically what happens is now you have processor, cache, and you have a bunch of things. Again, they're not bus-based, so they could be anywhere, right? Processor, cache. And then now you have a memory controller for each one. And the memory controller. And the memory controller. And memory controllers are distributed. So each memory controller can have a directory for the blocks that are in the physical memory over here, right? This is essentially main memory, I should say. So basically, now you have a distributed system. And each memory controller houses the directory for the memory blocks that are actually in the physical memory that is controlled by that memory controller. This way, whenever a processor wants to request some cache block that is housed over here, it needs to send a message to this directory over here. There should be some partitioning mechanism, mapping mechanism, and that gets the permission, and then this directory sends the data back, or tells, for example, this cache has the data, so it should send you the data, right? So that's what happens basically. So this is essentially, you're distributing the directory across the nodes this way, and that makes it scalable clearly, right? But it also leads to potentially longer message delays depending on the interconnect. It is scalable though. Okay. Let's share the screen again. So that's what this serialization location can be different for different blocks means. Okay. But now you can actually reason about, what's going on? Now you can actually reason about the protocol for a single block. Essentially, this is like a server client model, right? If you think about the directory, it's serving many clients. It's really a server for the block. It's serving, that's a directory node. And many clients are private caches. So now you can actually essentially provide proofs of whether or not this works using this sort of model. So directory receives read and exclusive requests and sends invalidation requests. Invalidation is explicit, basically, in this case. So if you think about the bus-based protocol, everything gets invalidated. And whenever you see a message saying bus read exclusive on the bus, you invalidate. So invalidation is kind of implicit in the message over here. But here, directory explicitly say you invalidate your blocks. And I don't care about anybody else. You don't need to invalidate your blocks, right? So that helps. Now the data structures are interesting. I'm not going to talk about a lot of this, but these are required to support invalidation and cache block requests. Essentially, you need to have, for each block, you need to have information about which cache has it in what state. So what I showed you earlier, the p+1 bits is just one example, right? That's a bit vector kind of data structure. You could have a linked list over here. So bit vector is maybe too large if your system is large. And if your share set is very small, for example, if the block is not shared by anyone, essentially you just need to have a null pointer or some indicator saying that you don't have this data shared or belonging to any cache. So why store a huge bit vector, right? So basically data structures matter over here. But all data structures need to somehow support the set inclusion test. Set inclusion test means who has the data. Somehow you need to actually ask that question to the directory, and the directory needs to be able to say that. And also what state a little bit. Maybe not perfectly, but at least you should distinguish exclusive versus shared a little bit, right? Assuming exclusive exists, and I'm assuming that exclusive states exist. That's important, right, for performance. So as I said earlier, false positives can be okay. You want to know which caches may contain a copy of block, and you may have additional invalidations if basically the directory says this cache may have the block, so I'm going to send an invalidation to it. That's okay. But of course, you cannot have a false positive if someone has the data modified, right? So you need to be careful again. That's what I mean by careful. So false positive rate, if you actually use a Bloom filter, for example, as part of your data structure, your rate determines your performance. So most accurate and expensive is the full bit vector, as we discussed. But again, you can have compressed bit vectors, because a lot of those bit vectors are zeros in the end, because a lot of the caches are much smaller compared to main memory, right? Imagine petabytes of memory versus, I guess, gigabytes of caches in a large-scale system. There's a huge orders of magnitude difference. As a result, a lot of the bit vectors are zeros. So you can compress the representation of the data structures. You can have linked lists, or you can have Bloom filters. You can have many different things. Okay, yes.
In the case where your cache line is too big and you have some location that belongs to different processors, but they are not actually accessing the same location, just accessing right? And then what you do, you reduce your cache line so that you can avoid this broadcasting the processor where you're sharing the same cache line, but they are not accessing.
So you reduce the size of your cache block only in that case? But now you need to provide support in your cache to be able to do that, right? You need to have either some sort of sectored cache or support for smaller blocks.
So you can reduce the invalidation, because I can see that in a case, for example, let's see one cache line, and then multiprocessor access indefinite location in this cache line. And then your
I understand. This is the false sharing problem that we discussed earlier, right? You have different locations updated by different processors in the same cache block. I mean, you can reduce it, yes, but in the end, now we have a reduced cache block, smaller cache block. And then the tracking granularity needs to be smaller, right? Basically, there's no winning out of the situation. If you have a sectored cache, for example, you may have a large cache block, but then you have you keep the coherence state in smaller parts of the cache block. Again, you have the same problem, basically. The directory needs to keep track of it at the smaller granularity. So unfortunately, the false sharing problem exists unless you go to the smallest granularity. Yeah, and that's a general problem with cache. Ideally, you would eliminate that by ensuring that different cache blocks have different data, right? Or you don't have two different blocks in the same cache block, right? Ideally, your data mapping should be to different cache blocks. Okay, So basic operations are essentially, the semantics are very similar to the Snoop-based system, but now you have explicit request and reply messages in the directory. So directory receives these requests that we have discussed, read, reads exclusive, and upgrade. It sends invalidation or downgrade requests to shares if needed, and forwards requests to memory if needed, and replies to the requester and updates the sharing state. So basically, this is all things we've discussed, so I'm going through this relatively quickly. But all of this actually makes the protocol design flexible, basically. Now you're communicating with messages as opposed to relying on broadcasts, right? You can now add new messages, basically. For example, exact forwarding paths depend on the implementation, and you can enable cache-to-cache transfers much more nicely with some messages. Again, this involves indirection, but it's a lot easier when you have a central coordinator. And you can potentially think about actually updating these protocols in the field. You can have actually a lot of processors, like I've suggested, one of the suggested reading is SGI origin. It's also in your readings. These systems are big multiprocessors of their times in 1990s, and they basically implement directory-based protocols. And a lot of these directory-based protocols are actually programs running in the memory controller. They call it the home engine, for example, or directory engine, something like that. Essentially, you can have micro programs running in the directory to decide what to do. And these can get updated also while the system is running, potentially, right? So essentially, in the field, you can actually change the protocol. Whereas it's much more difficult to do that with a Snoopy bus-based protocol because you're really relying on broadcast messages. First of all, you don't have a whole lot of options. And second of all, you need to bake those things into hardware because it's not like, the fact that you have a mediator enables you to make that mediator intelligent. Now that directory, it's a part of the memory controller, it can actually have some program running to actually serve these requests, right? Because it's again essentially a server. It's a client-server model. Like you can treat that program as a server program running in the node, in the directory node, and many clients are sending messages. And then once you receive this message, a program runs to decide what to do, right? So that becomes very, very interesting. And as a result, people have actually done a lot of, let's say, micro-programmed implementations of these directory protocols. So let's take a look at some examples over here of the flexibility. So let's say P0, processor 0 acquires an address for reading. It basically consults the home directory. Again, this is from Coherence. You can take a look at it. It consults the home directory, and the home directory has a decision to make. Should I supply this data exclusively to processor 0, or should I supply it in a shared state? Basically, do we set the exclusive bit or not, right? Again, this decision may be dependent on what else the directory knows about the system, right? Access patterns, etc. So you may have a sophisticated program running in the directory that observes the access patterns. Not so easy with bus-based protocols. You could implement additional hardware to do that, yes, but in directory, it's very natural. So, so the directory may actually decide to do this. It basically sends the data to processor 1, or basically it asks processor 1 sends the data to processor 0, right? Because it has some knowledge about what's going on in the system. That was an example of what I showed earlier also. So another example over here. Processor 0 sends a read exclusive request to the home directory of that node. And the directory knows that there's an owner, meaning exclusive access. These are different terminology. Unfortunately, different terminology is used by different books. This is from the same book. But this is basically some cache or some processor that has exclusive access to this block. The directory says, invalidate your block and send me the revised block back. That's what rev means in this particular case. If you read the terminology unfortunately is not consistent across many papers. But the revision means you send me the revised block. That's one option. Another option could be send me, well, actually, it could be that send me that you've done what you've done, and also send the data to the processor 0, right? So basically, directory can enable parallelization of things. Directory can send a message to the owner saying that invalidate your block and send an acknowledgement to me. At the same time, send the data to P0, for example. And then P0 may need to send an acknowledgement also, right? So it depends on the protocol design in the end. But you have this sort of flexibility. This sort of flexibility doesn't exist in a bus-based protocol unless you go and modify it significantly, right? Okay. So another example over here is contention. And contention happens, as we have seen in bus-based protocols earlier, the ping-ponging, for example. So for example, both of the processors, P0 and P1, send a read exclusive request to the home node for that cache block. The home node says, okay, processor 0, you have the data exclusively. And it basically needs to do something about processor 1. What does it do? Well, one option is negative acknowledgement, saying that processor 1, too bad you lost. You're not going to get the data back. Request from me later. That's one option. Another option would be to buffer the request, right? But this is clearly doable. And then later, clearly, one processor is happy, another processor is unhappy. And later, processor 1 requests, again, maybe with some back off. So there are a lot of contention resolution protocols that you can implement clearly. It's asked for the read. And then the home node now says, processor 0 has the data exclusive because I granted it earlier. It's asked invalidation for processor 0. And then basically, it can do something like this. Give me the data back, acknowledge it, and also give the data back over here. Or don't give me the data back, acknowledge it in this particular case, acknowledge the revision, and send the data exclusively to processor 1. Right? So that's the idea. So basically, it's very flexible, as you can see, right? You didn't need to do something exactly like this. You can actually do something else. But let's talk about contention over here a little bit. Essentially, this sort of contention issue introduces a lot of issues, not just performance issues, but also potential race conditions. It could be dangerous. But you can actually eliminate these by knacking requests. Basically, entries that are actually not available to be given to a processor. Basically, you can negative acknowledgement the request of that processor. That's what this means over here. You basically knack. You say that I'm too busy, or you cannot get this block right now, request it again. That's a knack-based protocol. This has its own downsides potentially because it introduces new traffic, right? Now you're knacked and you need to request again, right? What if everybody keeps getting knacked, right? Then they need to request again. So there are a lot of issues with contention resolution that we're not going to go into. You can take a look at the Color and Sing book. They don't go into a whole lot of detail, but there's a lot of research that goes into it. So in this case, original request or retries. Or you can buffer the request, as I said. You can queue the request and grant them in sequence, some sort of sequence, maybe in the order that you have received them, or some combination of thereof. Because what if your buffer becomes full? What do you do at that point? You start knacking, of course. So there are a lot of issues that come about, not just performance issues, but fairness issues like we have talked about earlier, quality of service issues. What if a processor gets knacked a lot, right? Then you have a problem over there. Which requester should be preferred when there's a conflict or a contention? And there are a lot of issues over here now, because especially if you have a scalable system, who gets the message earlier? And they all matter, right? For example, one processor requesting the data is only one node away. Another one node meaning one hop away if you have a network of processors. Another processor that's requesting the data is 10,000 hops away. Who do you prefer? Now, fairness is not just about who gets turns, but there is also a latency component to fairness, right? One processor is so far away and the other processor is very close. Like in this picture, right? If you remember, yeah, well, not that picture, sorry. Wrong picture. In this picture, these two processors are very close to each other, but this one is very far away from somebody else over here, right? Yeah. So basically, when you're building a very large scale multiprocessor, you run into a lot of interesting issues, let's say. At that point, and we're just talking about the directory accesses right now, right? And then there could be other issues also. Okay, ping-ponging is still a problem, actually. Ping-ponging still exists in directory-based protocols, but it's not as bad because directory hopefully is clever about handling ping-ponging. It can be reduced with a lot of protocol optimizations, basically. For example, if you have a lot of requests that are coming to a particular node, so if you remember the ping-ponging, let's get back to the one that I had over here. Yeah, if you have a lot of requests that are coming as read requests, now you can buffer them in your queue, right? And you can actually analyze them and you can figure out that, oh, there's something going on in this particular address, even if the program doesn't provide any information to you. And then it basically tries to serve the request in order potentially, right? So basically you can be a bit smarter about how you order the requests. Okay. But of course, a higher level synchronization can fix ping-ponging in a better way, potentially. But we're not going to talk about that. As I said, we're going to assume that the programs are properly synchronized. Proper synchronization is important at the software level, but high performance proper synchronization is even more important at the software level. Basically, how do you actually improve the performance of your synchronization parameters? That's really not the subject of this course. Yeah, take a parallel programming course for that. And I don't know which parallel programming course actually go into a whole lot of detail. How many people have taken parallel programming here? Have you got into a lot of detail on optimizing let's say, ping-ponging, getting rid of it at the higher levels, somewhat. I see somewhat, but yeah. Okay. Yeah, but basically, I think if you really want to optimize your parallel programs, it's really important to know what's going on in the coherence protocol also. Okay. Okay, so let's talk about some questions over here. Actually, directory cache coherence is a fun topic, and it's a fun topic to also have questions like reverse engineering. You will see some examples. I will discuss some in the context of what I'm going to discuss. But how large is the directory becomes a problem. As I said, this could be quite large, right? So we're going to do some calculations also. But if you have petabytes of memory or 1 exabyte of memory, and you have 64-byte cache blocks, basically the total size of the directory across the entire system is 1 exabyte divided by 64 bytes times whatever the data structure is that you're representing. So it's a function of your cache block size, your memory size, and the system size, how many processors that you have. If you have a bit vector, how many bits do you need to represent 1 million processors? It's a large number of bits, right? So basically that large number of bits that I don't want to calculate right now times log 2 to the 1 million times 1 exabyte divided by 64 bytes. That's the size of the directory. And that's a huge size, basically. Not so good. That's why people look at compressed representations, for example. How can we reduce the access latency to the directory? These are things that people have looked at, and we're not going to talk about that. But unfortunately, you have to go through the directory. So caching the directory helps with the access latency, but it complicates the system a lot. So I'm not going to go into that, but reducing the access latency, you can actually employ similar techniques, right? You can prefetch the directory entries, you can cache them, etc. They all complicate the system. But real systems actually do this. How can we scale the system to thousands of nodes? When you start scaling, all of these become issues. And can we get the best of snooping and directory-based protocols? Basically, that's what's usually done today, as I mentioned earlier. Usually you have some snooping parts. And then within 16 processors, there's some snooping that happens. But if you need to go out of that, you have directory messages that go to the scale to the system. So usually what we have is hybrid today. So there's heterogeneity. And there are also research papers. This is one paper that I would recommend. It's called Token Coherence. Its idea is basically to decouple performance and correctness issues. And it basically tries to get the best of snooping and directory protocols. I will not go into it in detail. There's actually a lot of literature over here, which we will not go into. This is a topic that has been examined a lot, especially in the 1990s and early 2000s. There are a lot of papers that you will see. Yeah, today it's not as hot, let's say, but I think there are some cases where it could be hot or very interesting. Clearly, it's important, but it's not necessarily the hottest research area because a lot of the biggest improvements are actually already done in coherence. Now, the question in coherence is, how does it adapt to modern systems? And we're going to talk about that, hopefully, if we have time. But this is an example question. And I like this sort of questions. You can take a look at it. Assume we have a processor that implements a directory-based cache coherence protocol we discussed in class. The physical address space of the processor is 32 gigabytes, very small, 2 to 35 bytes. And a cache block is 128 bytes. Okay. The directory is equally distributed across randomly selected 32 nodes in the system. So that's another thing that you can do, right? Not every node has a directory part. You find out that the directory size in each of the 32 nodes is a total of 200 megabytes. How many total processors are there in the system? Show your work. So that's basically simple reverse engineering. And let's do this question very quickly. I think an example answer is basically calculate the block per node first. So if you have 32 gigabyte address space and 128 bytes per block, if you divide this by this, you get the number of blocks. And if you divide by the 32 nodes, because the directory is distributed across 32 randomly selected nodes, this is the number of blocks that each directory node needs to keep track of. Right? That's a simple calculation. Now, you know that information. What is also given to you is 200 megabytes. So 200 megabytes is equal to whatever you store in a directory node. Now, that 200 megabytes can be expressed as 25 times 2 to the 23 bytes. Now, what does this mean? It's also 2 to the 25 times 2 to the 26 bits. Now, this is the directory storage per node, which means that the directory storage per block, you know that you have this many bits, and this many bits correspond to this many blocks. You just make a simple division, and that gives you 200 bits per block in a directory node. Now, assuming the directory scheme we discussed earlier, which is p+1, each directory entry has p+1 bits, so the number of processors is 199, right? Okay, it's a small scale system, as you can see, small memory, etc. But even so, if you think about this, clearly this is reverse engineering that you should do if you understand how the directory is distributed. But if you think about this is in this small scale system, we have a 200 megabyte directory storage per node. So it's actually a lot. 200 megabytes times 32 is 6.4 gigabytes, right? That's a lot. That's a lot of directory storage in the entire system. And our memory is 32 gigabytes. So it's actually 20% of your memory. Doesn't sound very good, but that's how it is. Now, if your system was much larger, imagine that 199 was 1,000,000. Now this would be much bigger than your memory. So directory storage is much bigger than your memory. So you basically run into a lot of issues with directory-based protocols in terms of storage. Even though they're very, very scalable, in terms of storage, they're not that, let's say, very, very scalable. And you need to basically play some tricks. At least storage like this, right? If you have 1,000,000 processors, having a bit vector of 1,000,000 may not be a good idea, right? Because almost all of them will be zeros. So keep that in mind. Okay, any questions? So cache coherence is interesting. I think I'm done with at least the basics over here, but there's of course a lot to cover. If you open Color and Sing book, it's a huge chapter. I think you'll get maybe 150 pages of cache coherence and maybe more after that. And if you're interested in the guts of cache coherence, I'd recommend looking into it. Unfortunately, it's from 1994. There's a later book by Michel Dubois, Per Stenström. They actually cover cache coherence in a much concise way. You can take a look at it also. But as I said, it's interesting. There's a lot of ideas that have been proposed. A lot of them have not necessarily been implemented in real systems because it's already a very complex part of the system. Adding more complexity is something that, I mean, as we discussed in earlier lectures, adding complexities in general is not what people want to do, right? But people are even less motivated to add complexity to an already complicated part of the system. So if it's relatively simple, they don't want to add complexity. But if it's already complex, they definitely don't want to add complexity. So in general, in systems, this is a part that doesn't get touched a whole lot, unfortunately, even though there may be ideas. And usually, if you develop an idea, you should definitely check the literature of 40 years in cache coherence, because probably your idea is going to be very, very similar to one of those works, unless you take a different approach. Now, I'm going to show you an example where people have taken a different approach. This is a relatively recent paper from these folks, Microsoft and Michigan. And they basically showed that, this is actually very interesting. I think it appeared at ISCA 2022. But basically, they showed that using coherence protocols, you can do RowHammering, which is actually interesting. I'm not going to go into details of it because we don't have time, but they basically say they discover a novel form of hammering that they refer to as coherence-induced hammering, caused by Intel's implementations of cache-coherent non-uniform memory access protocols. Okay, I guess I'm not going to go into it. You should take a look at it, basically. Basically, because of the coherence accesses, you get hammering in this particular case, and it's related to directory implementations. And the way, I mean, they don't explain it a lot here, but the way they fix the problem is basically by changing the coherence protocol. They basically say Moesi prime. If you really want to know what it is, you can take a look at it. So according to them, they demonstrated on, I assume, Microsoft's, like on a major cloud provider's production hardware. They basically say that in commodity benchmarks and essentially dirty sharing across NUMA nodes, non-uniform memory access nodes, which is essentially what we had over here, right? Here. So not that one. So this is a non-uniform memory access system. What does it mean? The latency to access this memory from this processor is faster compared to the latency to access this memory from that processor. Basically, because the memory is distributed across the system, the latency to access is very different for different processors, for different chunks of memory. And they basically say that because of the dirty sharing that happens across these nodes, you get a lot more activations than what is actually seen in RowHammer thresholds to induce bit flips. Again, I will not go into detail, but if you actually look at the problem in different ways, you'll discover other issues, as you can see, right? Which I find interesting. Any questions? Thoughts? Okay. Okay, so maybe I will also talk about another recent example. Basically, remember, we were talking about processing in memory, and we were talking about potential barriers to adoption, and coherence was one of them. And this is actually one of the hairy issues, because once you start extending processing in memory or do computation on the memory side, now whatever data that you're modifying on the memory side also needs to be coherent with what's in the CPU side, right? So now your coherence domain extends. Now the question is, how does coherence change when you go into a near data accelerator system or processing in memory system? And we tackled this problem a little bit. We have 2 papers. I believe this is really the state of the art work in this area. Unfortunately, not many people touch this area. Let's say I think more people should touch this sort of area within the context of new processing paradigms like processing in memory. I'm going to talk about this work a little bit because I think this is really important going into the future. And the nature of the problem a little bit changes because, okay, coherence is expensive, no question about that. But once you ship something to memory, your goal is to really ensure that the data doesn't move, right? But if you need to get permissions for coherence from a directory, for example, now fundamentally you're causing data movement or movement of requests, let's say, from the memory to somewhere else. Essentially, this eats away from some of the benefits of processing in memory, as this work shows. So, okay, let's go through this relatively quickly because I think a lot of these are background. I just copied and pasted some of these slides. You can take a look at them on your own. But basically, this work is trying to provide coherence to near data accelerators. Essentially, when you offload some computation to a compute unit on the memory side, clearly you have large cost of off-chip communication. And these applications generate a large amount of off-chip data moments. And it's impractical to use traditional cache coherence protocols because when you want to modify some data, do you really need to tell everyone else over here? Assume that directory-based, for example. It kind of doesn't make sense, right? Because you overcome a lot of the downsides. Basically, you're trying to reduce data movement, but now you're creating some additional coherence overhead. So basically, this paper doesn't look at directory, but it looks at really a coherence protocol at a higher level, let's say. It looks at 3 different mechanisms, and it basically shows that a lot of the existing coherence mechanisms eliminate a significant portion of the benefits of processing in memory. And the majority of off-chip coherence traffic is actually unnecessary. So these are some of the sort of optimizations that you can do. If you can realize that off-chip coherence is unnecessary, maybe you do coherence at a coarser granularity, as this work does. And much of the off-chip traffic can be eliminated if the coherence mechanism has insight into the memory accesses. We will see what that means. Basically, you keep track of which blocks are read and written, and you basically do a coherence check in bulk across those blocks. So it's going to be similar to some of the transactional memory mechanisms that I'm going to mention at the end. So basically, it's going to be an optimistic approach. Optimistic means you have some processor, and it optimistically assumes that it has permissions to update the blocks and read the blocks, for example. This is optimistic versus pessimistic concurrency. I want to get back to this at the very end of the lecture, hopefully, if we have time. But optimistic concurrency says, I want to optimistically assume that I have permissions, and I want to actually do the reads, assuming that no one else is going to read from that, right? That's the assumption. But if your prediction is wrong, you basically are going to say, oh, you need to detect it. And you need to say, okay, I did something wrong, so I'm going to roll back and re-execute. That's the idea. So you'll see this more basically. So basically, the idea is to gain insight before any coherence check happens, because coherence check is expensive. If you want to check every single cache block, you need to go through the bus. So before that, we want to identify what kind of read and write accesses we're going to do, and perform only the necessary coherence requests in bulk together. And that's the idea over here. So let's take a look at it. So basically, this work gives the results for it. Essentially, this comes within 10% and 4% of an ideal NDA coherence mechanism where you don't actually request permissions at all. So, okay, I'm going to skip the near data processing background because you all know all of that. So let's take a look at some applications. So if you want to do near data processing, applications require partitioning across CPUs and main memory. For example, memory-intensive portions benefit from processing in memory, but compute-intensive or cache-friendly portions should remain on the CPU. And that's what leads to the coherence problems, basically. So this paper observes that CPU threads often concurrently access the same region of data that NDA kernels access, which leads to significant data sharing. So, and then the second key observation is that CPU threads and NDA kernels typically do not concurrently access the same cache line. So there's false sharing, actually, if you think about it in the region. Okay, so basically, the CPU threads rarely update the same data that an NDA is actively working on. But this doesn't mean that you should not get the coherence request, because there's a potential that somebody's going to update that data. Right? So this work goes on to analyze 3 existing coherence mechanisms. One is non-cacheable, bad idea in general, as we discussed. Mark the NDA, only the data that the processing in memory system is going to operate as non-cacheable. Coarse-grained coherence is what we discussed earlier, basically. Get coherence permission for the entire NDA region. This could be a huge set of pages, right? It could be, I don't know, 10,000 pages. It could be 1 page. Basically, it's a coarse granularity coherence. This means that you get the coherence permission for the entire coarse granularity, and then you lock that, and then you work on it, and then you unlock it, and then somebody else can have it. And then fine-grained coherence is basically traditional coherence protocols like MESI that we discussed. In fact, it's MESI in this particular case. So let's take a look at the non-cacheable approach. So you mark the NDA data that the processing in memory PIM system is operating on as non-cacheable, meaning that CPU never cached it, right? Okay, this doesn't sound very good because you're not taking advantage of the cache hierarchy of the CPU for workloads that benefit from it. As a result, you generate a large number of off-chip accesses and significantly hurt CPU threads performance. And it's actually very bad. It turns out, even if you do offloading to memory, with this sort of coherence approach, you don't get any energy saving, and you perform worse than CPU only. So you partition your workload, you do the hard work, partition your workload between the CPU and processing in memory, and you lose performance and you don't get any energy saving because the coherence over it is very bad, right? So that's why non-cacheable approaches are actually quite bad in general. Coarse-grained coherence is going to do a little bit better, but basically the idea is to get coherence permission for the entire NDA region. So whenever NDA is going to operate on a region, CPU flushes all of the dirty data related to that region. And it turns out this leads to a lot of unnecessary flushes of a large amount of data, especially in applications that touch a large amount of data. And they essentially use coarse-grained locks to provide exclusive access. So this is basically the idea. CPU stalls when it's accessing some region, and NDA can operate on that region, essentially. That's the idea. So I'm not going to go into how you support it, but you can support it with some mechanisms today. Unfortunately, CPU cannot access these locations, basically, in that case, even though it may not be accessing the exact cache blocks that the processing in memory engine is accessing or updating, right? So it turns out this doesn't provide any performance benefit and performs worse than CPU only, but not as bad as non-cacheable. It does provide some energy benefit, as you will see in the results later. So non-cacheable is worse than coarse-grained, and this is actually true for non-processing in memory systems also. In general, if you go to non-cacheable, you're eliminating the benefits of caches. Coarse-grained, you're still keeping some benefits of caches, but maybe stalling a little bit, right? But still, not so good, right? You have a processing in memory system that's supposed to provide performance and energy benefits, and you're not getting any performance benefits in this particular case. Maybe you're getting energy benefits, but you could do better. So fine-grained coherence is something like MESI, like we've discussed. So here, it actually is simpler. So the programming model is simpler. Whenever you program whatever you offload to the memory side, you don't need to think about coherence as much, fine-grained, coarse-grained, or non-cacheable. You just basically is part of the coherence domain. It allows the NDA or whatever is accessing the data to get permissions only for the pieces of data that are actually accessed at the cache block granularity, of course. False sharing at that granularity still exists. Okay. So basically, this still leads to high amount of off-chip coherence traffic because this is very fine grain, right? So if you look at it, things that are memory intensive are offloaded over here. So it needs to get coherence permissions it needs to communicate coherence permissions across the bus. And it turns out, it eliminates a lot of the benefits of energy benefits of the ideal processing in memory mechanism. So in terms of performance, it's better than the others, as you will also see in the results, but gets rid of a lot of the energy benefits. So basically, not having some coherence mechanism that takes into account the fact that there's a huge bus and expensive communication medium between a processing in memory engine and a compute-centric engine gets rid of a lot of the benefits of processing in memory. And that's why coherence is actually a major challenge in these systems. Okay, so these are the results. If you're interested, I will not go into a whole lot of detail, but you can see that fine-grained coherence is the best in terms of performance, but ideal NDA is much better. And these results are actually, speedups are relatively low because we were able to simulate only a small amount of data sets. I'll give you some large data sets results, which are much better. But again, the trends remain. Fine-grained coherence performs maybe okay, but it's not as good as an ideal mechanism without coherence overheads. And you can see that other approaches to coherence are pretty bad. Non-cacheable and coarse-grained. And this is CPU only. Okay, and this is the energy. So if you look at energy, non-cacheable is terrible because you actually lose energy. Coarse-grained saves some energy. Fine-grained doesn't save a whole lot of energy. So energy benefits of processing in memory gets eliminated by a lot of coherence mechanisms. So ideally, you would like to, you want to get ideal energy benefits and ideal performance benefits. Okay, so the question is, how do you design a coherence mechanism? And this is basically a challenge, research challenge. I'm not going into individual details over here, but because we already discussed the reasons why these are bad, actually. So basically, the goal is to really fix the problem. And I believe there's actually more to do. You will see that the mechanism that we introduce works okay, but it's complex. So I think there needs to be more efficient mechanisms going into the future. So we've already discussed this. And the majority of off-chip coherence traffic is unnecessary. And the goal is to design a coherence mechanism that retains the benefits and enforce coherence with only the necessary data moment, as much as possible, of course. So that's the idea of Conda. And this is an optimistic execution engine. It's going to be very similar to the transactional memory proposals with one key difference. Essentially, we're going to enable two observations, having insight into what accesses are done by speculatively executing the near data processing program, enables you to figure out what is unnecessary coherence traffic, basically, enables you to eliminate the unnecessary coherence traffic. And the main reason is you have a low rate of conflict between the CPU threads and NDA kernels. Basically, you're operating on some data in the CPU and processing in memory. There's potential that they're going to conflict in some cache block, but in many cases, they're not going to conflict in the cache block. Okay, so the basic idea is the processing in memory engine executes the kernel. It assumes it has coherence permissions. It basically keeps track of what accesses it does. And when execution is done, it checks whether it has done the right thing, let's say. It performs only the necessary coherence requests. And if in the meantime, it didn't need permission, meaning that the processor did not touch any of the cache blocks this processing in memory engine touched, it's okay. Basically, you speculatively execute it. You assume that you had coherence permissions, but nobody else touched those blocks, so that's okay. That's the idea. That's the beauty of optimistic execution. You speculatively execute, assuming that you don't need coherence permissions. And if you actually didn't need coherence permissions because nobody else touched those cache blocks, that's good. But if you actually did need coherence permissions because someone else touched the cache blocks in a way that makes your data wrong, that's called a data conflict, then you need to roll back the execution of the processing in memory engine in this particular case. So let's take a look at the high level. So you have a CPU thread that's executing. It launches, it basically offloads a function, let's say, to processing in memory. Processing in memory does optimistic execution, and CPU thread continues executing. So there's no coherence request during this time. So fine-grained coherence basically requires requests for every single block, coarse-grained and non-cacheable handle it in different ways. But here we have no coherence request. We're optimistically assuming that we have the permissions. And at the end, you have a coherence resolution. You either commit the results, which means that you need to buffer them before you commit them, or re-execute this kernel. Commit means you commit the results, assuming that there was no conflict between these two executions. And you re-execute means that you assume that basically you find out at the end over here that there was some data conflict. So we're going to take a look at that. So if you think about this, actually similar to transactional memory mechanisms today. How many people know about transactional memory? Okay, good. How many people do not know about transactional memory? Okay, fine. I'm going to talk about that later on. I won't talk about this. But it's the existing transactional memory mechanisms are actually optimistic concurrency also. You basically delineate transactions in your program, and these transactions are executed optimistically across different processors, not basically think about multiple different CPUs. And there is a mechanism in software or hardware or cooperatively in software and hardware that keeps track of which processor touched which cache blocks. And at the end of the transaction, basically you have a commit transaction phase. A check happens, if any other processor conflicted with the data that you touched within this transaction, you're going to roll back the transaction. Or something is going to happen in the system. Some transactions are going to be rolled back so that you don't get the wrong data. No one gets the wrong data. That's the idea. This simplifies the programming model of lock-based programs. And this was developed in the early 1990s, actually. I will mention that later on. So it's very similar to that model, except CPU never rolls back, if you think about it. So our goal was to actually integrate NDA with any CPU, so without any CPU support. So CPU never needs to roll back. Okay, so that's the idea, basically. I will a little bit go into detail over here, but basically you have no coherence request. So how do you keep track of what you have touched? So basically you need to keep track of the things that you have touched in a signature of blocks that you've read and written to in the optimistic execution in the near data processing engine, as well as in the CPU. And then at the end, you send the signature of the blocks that you've touched, address signature, and then that signature gets compared to the signature of the blocks that this CPU thread touched. And if there's any data conflict based on the comparison of that signatures, you either commit or re-execute. That's the idea. Yes, exactly. It's only at the end of the execution of the in-memory processing in-memory kernel.
Then it's get worse according to the size of the.
Exactly. Yeah. Exactly. Yeah. And the paper discusses all of those issues. Basically, if the size of the kernel is huge, the probability that you may have a conflict between these CPU and NDA executions may be higher. Right? Depends on the program. But yes, if you normally execute a whole lot of code, you're touching a lot of blocks likely, and that may lead to a conflict. And that's a traditional trade-off in transactional memory also, as if your transactions are larger, the probability of re-executing or conflicts increases. Yeah. No, you need to get coherence permissions at that point.
Yeah, but if the CPU wants to data that was the signature just to get about just to complete something, just to read, and the processing memory actually pulls it.
Yeah, I see. Basically, maybe you can use some of that, but that requires you to identify which data is trustworthy and which data is not. Basically, which data is correct and which data is not correct, right? So the re-execution is completely blind. They re-execute everything. I mean, there is actually literature is filled with methods that try to identify which data you can. How can you minimize the re-execution overhead? Those are usually very, very complicated in general. Okay, so let's talk about how do we identify coherence violations. Basically, coherence requests are only necessary if both the NDA and CPU access a cache line, and at least one of them updates it. So if both of them read, no problem, right? The problem happens with updates, clearly, right? Basically, there are three examples. Let's take a look at them. So if NDA reads and CPU writes, there's a coherence violation, clearly. If NDA writes and CPU reads, actually, there's no violation. NDA writes and CPU write, there's no violation, because these can be reordered across them. And you can read the paper for more detail, but I'll give you some example over here. So assume that CPU does write to Z, and then read to A, write to B, and then NDA does read to A, and then read to Z at some point, right? So you check at the end of the NDA kernel, which is assumed to be here, any coherence violation. In this case, there's no coherence check during NDA execution. Now, NDA reads old value of Z. In this particular case, yes, because NDA read some value of Z that was updated by the CPU, right? So you flush Z to ZRAM and re-execute, essentially. So this is another example. Here, you write to Y and read from Y. There's any coherence violation. Coherence check happens at the end of the NDA kernel. Now, because the NDA kernel did not read from Y at all, there is really no coherence violation over here, right, if you think about it. So you can commit this operation over here. Of course, there are issues with the memory consistency model over here. You need to ensure that memory consistency also is handled, but we're kind of ignoring that over here because consistency and coherence are different issues. But assuming that this satisfies the consistency model, there's no coherence violation over here, if you think about it, right? You need to think about it a little bit. So this write over here doesn't necessarily conflict with this write because there's no reading of the data that happened in the NDA. So NDA did not really use the data wrongly. So, and then at this point, you commit the NDA operation, so you need to actually merge the data that happens. And C4 and C5 are assumed to be ordered before N5 over here. Okay, so you need to think about it, basically, how to make it work. So there's architecture support that's needed over here that I will not talk a whole lot about. You can read the, yes, please. Oh, okay. So here your CPU is writing to some block and NDA is reading from that block, right? So you may not actually, you don't get the correct data over here. At least you don't know if you have the correct data, right? That's the problem basically. So what happened was, if you go back, well, I don't think this shows it. Basically, there's no coherence checks over here. You read the block, CPU wrote to that block. In the CPU's cache, there was a new value of block. NDA read an old value from the memory because it didn't try to access the cache during the execution. At the end of the execution, it says, oh, I read this block, and the CPU also keeps a track of what it has written to and read. CPU checks, oh, I wrote to this block. You shouldn't have read that block because you read something off the memory that was old. Does that make sense?
Yes. So
Yeah. What do you mean different time? So this happens after CPU sends an NDA execution. Yeah. So if you go back to this model, let me go back. Maybe that helps. So basically, you offload to NDA kernel and you start keeping track of the signatures. And here you also keep track of the signature, and then you do the comparison at the end. So you don't know what time the CPU updated, and you don't know what time the NDA read. Yeah, because you're doing it at the end in a coarse-grained manner. Yeah.
the coherence check is done at runtime.
Yeah, everything is done at runtime. Yeah.
Can you do it at runtime? Because
Oh, okay. Well, I mean, you don't. Maybe a compiler can help this, right? But in the end, that requires a lot of analysis.
it will eliminate some of the
Yeah. Yeah, potentially. I mean, if you can, I don't know. It may not be that easy. Okay. Okay, so let's take a look at the architecture support. So this requires clearly some support. You need to, on the NDA side, you need to have the read set and write set. And we assume actually there are some caches on the NDA side, as we have discussed earlier. And on the CPU side, you need to have the write set and then coherence resolution unit. And we can eliminate the read set over here. You can read the paper for more detail. Basically, these are the additional things that you need to have. So it's not cheap, let's say, but it's not that expensive also, as you see. There's also a per word bits over here. So there's actually a little mess because you need to ensure that if you're not going to commit the data, you've written to the data, but you haven't verified that you can actually write to the data because you don't necessarily have the coherence permission yet. You need to have some speculative bits in the caches to mark those updates. Eventually, you may commit them. Okay, so I've already discussed this. Read set and write set are used to track memory access from NDA, and the CPU records all writes in the CPU write set. And these signatures are actually, you can think of them as bit vectors, but you can actually construct Bloom filter-based signatures. It's actually a Bloom filter-based signatures, similar to the Bloom filters that we have seen earlier in this course when we talk about radar, for example. Yeah, so it basically enables easy coherence resolution with simple bit vector-based operations. And it also allows for a large number of addresses to be represented in a fixed length register. So you don't have a list of addresses. It's really a bit vector representing what you have touched in the read set and write set and the CPU write set over here. Okay. So this is how you detect the conflicts. You compare the CPU write set with the NDA read set, essentially. And if there is no conflict, then what you do is any clean cache lines in the CPU that match an address in the NDA write set are invalidated, and NDA commits data updates. So it requires some more work, basically, even if there's no conflict. If a conflict happens, the CPU flushes the dirty cache lines that match address in the NDA read set, and NDA invalidates all uncommitted cache lines. So it's actually a bit messy because you need to go through your cache to actually flush things. So there's overhead associated with it. It's not a simple, I wouldn't call this a simple mechanism, essentially. That's why there's need for more research in this area. And then NDA invalidates all uncommitted cache lines because it didn't have permissions to at least one thing over there. And then signatures are erased and NDA restarts execution. Okay. So I will not talk a lot about evaluation, but basically it's the reality of the full system simulator. And essentially there are a bunch of applications. You can read about them. Essentially, we already discussed that. But basically, the benefits of this mechanism is not that bad, let's say. It gets close to ideal and much better than existing mechanisms for coherence. And I think you can read the results. Memory system energy is also good. You can see that, well, these are some analysis, but you can see that we're very close to ideal NDA. So not that bad also. The issue is really complexity. And there's also more analysis in the paper. This becomes, actually, the issue is not just complexity, but as you scale the system to a large number of memory modules, the difference between ideal and Conda also starts diverging. So basically, you're not as close to ideal anymore as your memory size grows. So that's also expected kind of, because now you actually start having a lot of communication. And there are other results in the paper, as I mentioned, for larger data sets, which you cannot simulate for that long. Let's say you get a lot higher benefits, as you can see, and there's a lot of sensitivity analysis that you can look at. Okay, I will not talk about this again because we're almost out of time. Any questions? So, I mean, as I said, this is the state-of-the-art work and doing coherence for processing in memory, which is even messier for, let's say, doing coherence for CPUs. And it's good to think about that, I think. There's more to be done in this area. Now, based on what we discussed, I will very quickly mention, we have about 4 minutes, that's good. Optimistic concurrency, we've kind of discussed this essentially, but the idea of optimistic concurrency has been developed since 1980s. And this is a seminal paper by Morris Hurley and Elliot Moss on transactional memory, essentially. It introduced the notion of transactional memory. There are earlier papers that talk about optimistic concurrency, especially in databases, for example. But this is looking at main memory. And the idea over here is the programmer specifies code to be executed atomically as transactions. And the hardware and software guarantees atomicity for transactions. So basically, you have a piece of code, transaction begin, transaction end. And then another piece of code, transaction begin and transaction end. The programmer assumes that this will be executed atomically. And it's the system's, hardware and the software's job to ensure that either the entire transaction is executed or none of it is executed. That's what atomic means. And this is nice because this is what you want in a critical section, right? Either you execute the entire critical section or none of the critical section, right? And this basically gets rid of a lot of issues with lock-based programming. And this was motivated by the difficulty of lock-based programming and also motivated by the lack of concurrency in blocking synchronization. So pessimistic concurrency is essentially usually called blocking synchronization. Pessimistic means that you assume that you don't have the permission, so you don't proceed. Now you're pessimistic. You're not speculative, essentially. You're waiting to get the permission, which means that by nature, you're serializing things a lot, right? You're waiting, essentially, right? So, and that reduces your concurrency in a system. But the question is, are you really waiting for something that's really important, or are you really waiting for something that's not important, right? Transactional memory is motivated by the fact that in many cases, you may be waiting for, so two transactions may be executed, and they may not be touching the same cache blocks at all, right? So that happens, right? If you have a larger grained lock, for example. So basically, there are a lot of issues with locks. Like you can underlock, you get data erases, you have deadlock issues, you have blocking synchronization like pessimistic, and you have conservative serialization as a result. Transactions actually make the interface simpler. You can reason about transactions better, and you don't need to think about what do I lock? Which locks do I acquire in order to actually update some part of a data structure? You can actually have a single lock locking the entire data structure, but that usually leads to very large serialization because of the blocking synchronization of pessimistic locking, right? So normally what people do in lock-based programs is they try to have very fine-grained locks, hierarchical locks, all kinds of different locks. Now, if you actually go to very fine-grained locks, it's very easy to forget the locks, for example. And then there could be ordering issues. I acquired lock A, lock B, lock C in this order, and I need to release them in some order. If you forget to release one of them, then you run into deadlock issues and maybe ordering problems also. So transactions actually get rid of all of those problems and make those problems the system's problem, right? Programmer, you don't need to worry about that. System, good luck dealing with this. And that's one of the reasons why transactional memory is a great idea for programming. Unfortunately, it complicates the system a lot. And it's implemented in existing systems, but you may have seen that there are serious bugs in existing systems and transactional memory implementations. IBM has actually a beautiful implementation in their Z series. You can take a look at that. I have it in one of the lectures that I reference. But basically, it's a non-blocking. You either do all or none. All of the transactions can start executing, and somebody checks whether they've actually acquired the permissions. And you get serialization only on conflicts, basically. So it's very similar to what we have discussed earlier, Conda. you execute both pieces of the program. At the end, you check. And if somebody got the wrong data, you roll it back and re-execute. Maybe everybody re-executes if everybody got the wrong data. Right? So essentially, locks are pessimistic concurrency. Transactions are an example of optimistic concurrency. Okay, I think I already said this. So you need some basic mechanisms like tracking reads and writes per transaction. Detect when a conflict occurs between transactions. You need to record new and old values somewhere, just like we did in Conda. You need to say, okay, this is a speculative value. I cannot commit it to memory until I know that I can commit it to memory. So this is called version management. And then as Thomas, you commit new values or abort back to old values. So there's old or non-semantic. So these actually complicate the system. If you think about it, the system support you need to provide for it is you need to do checkpointing, for example, for atomicity. So there are a bunch of issues I'm not going to talk about. So there's another reading that I will recommend in terms of optimistic concurrency. I think we're almost out of time, but I will mention this. This is actually a speculative form. The idea is to elide the locks. And basically, these folks realize, like many other folks, that dynamically serialization of locks may be unnecessary because critical sections could have safely executed concurrently without locks. And this doesn't happen in current processors because you cannot dynamically detect these dependencies. So, okay, this is inserted in the wrong place, but you can find lectures also. So basically, many locks are unnecessary, dynamically at least. Statically, they may be necessary, but dynamically, they may not be necessary. They may be sometimes necessary, dynamically. Stores occur infrequently during execution. Updates can occur to disjoint parts of the data structure. Right? The idea here is to speculatively assume that lock is not necessary and execute the critical section without acquiring the lock. Check for conflicts within the critical section. And if your assumption is incorrect, roll back, basically. I've done the wrong thing. And this is usually building on coherence protocols in general. So these are some examples. For example, I like the second example over here. One processor is locking the entire hash table, even though it's actually updating one bucket. Another processor is locking the entire hash table. It's updating some other bucket. Normally, these could execute concurrently, right? Clearly, there's no reason. The reason why is locking granularity is too high, right? If you had basically here, you can speculatively execute both of the locks, and you would get the data correct with that speculative execution. Okay, so I would recommend looking into this paper. Since we're out of time, I'm not going to read these, but you can take a look. This is actually implemented in Intel Haswell. It's actually a simpler approach than transactional memory, but it has a lot of the overheads of transactional memory also, as you will see. So in general, the idea is to execute threads unsafely in parallel. This is basically, these ideas that we've discussed are examples of speculative parallelization. And the main idea is to execute threads unsafely in parallel. Threads can be actually from a sequential or parallel application. We look at parallel applications, but it could be from sequential. Hardware, software monitors for data dependence violations. And if data dependence ordering is violated, offending thread is squashed and restarted, essentially. If data dependence are not violated, thread commits. If the threads are from a sequential order, then you need to preserve the sequential order, of course. So there's a lot of interesting things over here. I used to cover this actually in a more, let's say, advanced course. We don't have time over here, but there are a lot of very, very interesting ideas that people have developed in speculative threading and speculative parallelization. So I'd recommend you to take a look at the videos. We don't have time. And actually, there are a lot of other ideas also. There are multiple different lecture videos you can look. This was a time when I used to do hybrid or flipped classroom, let's say. Didn't work too well. Okay. I think we're already out of time. So if you have questions, any burning question, really burning question? No? I have to run to another lecture, so take your questions for tomorrow. Tomorrow we will discuss interconnects. Okay, take care.